Okay, hello everybody. Can you hear me okay? I can't tell if those speakers are working otherwise. Good, yeah. All right, welcome to the fourth version of the Omnidirectional Computer Vision OmniCV workshop. I'm just going to give a bit of an introduction first before we start in the keynote speakers. Okay, yeah. So let's figure this out. Should work now. Okay, so we've arranged a keynote speakers today. I think quite impressively kind of across a variety of different topics. So Wolfgang's going to talk about some like extracting geometry from omnidirectional cameras. Adrian then will talk about audiovisual aspects of 360 scene analysis. Right over to Robin, who's going to start the session, who's going to talk about image quality in fisheye cameras. So really looking forward to that. Unfortunately, Jacob last minute couldn't join us due to unforeseen problems. But luckily, Shubanker from why is that not clicking on? Yeah, from Qualcomm. So his colleague in Qualcomm is going to take over that keynote for us. A note to our workshop organizers, particularly big shout out to Kavya, who did all the heavy lifting for us here. And unfortunately, criminally, due to Canadian visa issues, she's not able to join us. I think it's insane how the visa issues have impacted so many attendees at the conference, but okay. So there's myself, Lee here beside me from Meta, Mark, who couldn't join us this year but has been heavily involved in the organization. He's with Yembo. Jonathan is again back in Ireland, and he's with Valio. Actually moved to Jaguar Land Rover now, but that's okay. Varun, one of our many Qualcomm organizers. So we've got Fatih Porkli, Shubanker, Pierre. No, not Pierre's with Meta. Central, all organized from Qualcomm. So a lot of Qualcomm influence here today. And a shout out to Ash and Stefan from Spleen Lab as well. So Ash will be chairing the second half of this workshop. Shout out to our sponsors. And so Lero sponsored a lovely set of really nice set of t-shirts for us. They're somewhere in these buildings. I've been trying to find out where they are. I've been trying to get them to this room. So if they arrive before we finish up today, you'll get a lovely kind of nice high quality t-shirt, OmniCV t-shirt. But fingers crossed we actually get them, because I have no idea where they are and I've been trying to find them. So Lero at the Irish Software Research Centre, based in Ireland, 400 plus researchers, a very large centre in Ireland. That's the contact details if anybody wants to reach out to them to talk about collaborations. Qualcomm, of course, did I mention Qualcomm before? So Qualcomm have sponsored our Best Paper Award. So thanks Qualcomm for that. Valio and Parallel Domain sponsored the Woodscape Challenge. So it's one of the 3 challenges we'll talk about today. The Taiwan AI Center of Excellence sponsored the MBL Challenge. So Enrique Bolivar is going to speak about that later on. And Spleen Lab have sponsored the Omnidirectional Drone Challenge. So Ash is going to talk about that later on in this session. Proceedings, I'm not going to go through all of this. But we have 10 published papers. I think the acceptance rate was about 60, a little bit over 60%. This year compared to last year, we got a lot of very high quality, not compared to last, but the submissions last year were also very high quality. But this year is particularly high quality submissions. So we've got 10 papers here. They'll all be presenting posters later on this evening, which I would encourage you to really go and have a look at, please, because they put a lot of effort into the papers, obviously, so we should do them justice and make sure we go and talk to these guys at their posters. So that's a bunch of that's the proceedings. So I'm going to hand over now to Robin, who is joining us via Zoom. Robin, if you can share your screen now.
Yeah. Does that work?
I need to put that on this. You give us a second, Robin. We can see you, but we just need to put you on the right screen here.
Full screen, maybe. Oh. Is it? Oh. Here. Maybe I just. So he's remote, right?
So while we're starting that up, I'll just introduce Robin. So Dr. Robin Jenkins is a distinguished engineer and lead imaging scientist at NVIDIA. His work has a strong emphasis on imaging quality analysis, modeling, and technical assessment. He's on the board of directors and is vice president for the Society of Imaging Science and Technology, so the ISMT. He is the IEEE 2020 secretary and project image quality for viewing lead, and is a visiting professor at the University of Westminster within the Computer Vision and Imaging Technology research group. Robin's going to talk today on aspects of image quality of fisheye cameras. So I'll hand it over to Robin now. You can go ahead, Robin, there.
Thank you so much. So hopefully folks can see my screen and you're all set up and you can hear me well.
Yeah, we can.
Oh, wonderful. It's a pleasure to be able to join you guys today about to talk to some ideas on image quality of fisheye lenses. So I'm going to start off with the video. I really work as an image scientist at NVIDIA and advise my colleagues across the company on what imaging systems are capable of. So as I introduce my talk, I just want to share this video with you and show you how we use some wide angle and fisheye cameras in our NVIDIA Drive platform. And they really help us to sense the world around us and act as eyes for our drive-in, our surround view, some in-cabin, as you can see, and we'll see, and some of our parking systems as well. So really, imaging systems have moved from producing beautiful pictures over the last few years on cell phones to being safety critical components of many safety-based systems. Self-driving cars we can see here, but also medical, industrial, and home robotic systems. One of the real challenges we face is how to justify some of the choices that we make as camera and algorithm engineers, and when we're selecting components, say, such as lenses and sensors. So how do we begin to rank the performance of cameras without incurring the cost of building every single combination of components that we could have? For a particular application, I might have to trade bigger pixels, for example, with more sensitivity for resolution and smaller pixels, or in the case of our fisheye lenses, more field coverage for less pixels on target. Another compounding factor, I personally see a fair number of computer vision papers that don't really consider the quality of input images and how it may affect results that we get from algorithms, especially at the limits of performance, such as low light. So really today, what I want to do is introduce one or two existing image science ideas that may help to influence the assessment of algorithm performance. So it's just finishing off here with some parking. Okay, let's move on to some guiding principles. So really neurons are decision engines and neural networks are hyperdimensional decision engines, and really giving a network more objective information about a scene or a target should help us improve decision making up to a point. After we get to optimum decision making, there's going to be diminishing returns. So the premise is that a camera that's able to provide a neural network with more information is desirable. After that, you're wasting resources such as bandwidth, compute, memory, thermal budget. So the main advantage of the fisheye camera is field coverage, and you're able to survey a wide area in a single image, so we don't have to search it as much. But the drawbacks are distortion, resolution on target, and image illuminance fall off at the edge of the field of view. Largely distortion-free images can be produced kind of up to about 120 degrees field of view. And beyond this, distortion is really kind of unavoidable. We can describe the distortion, of course. This is nothing new to folks here. We can plot incident angle, theta, against the distance, the radial distance in the image for a given focal length. And there's a number of standard mappings that are well known, from standard through to orthographic. And we can plot those on a graph as well. So we can plot relative linear radius versus incident angle. There's a number, these standard mappings have advantages and disadvantages, such as preserving the ratio of solid angles or distances, but we can essentially create any mapping we want. Also, generally, as we go from rectilinear at the top to the bottom, the distortion gets worse. Another part of the pathology of fisheye images is generally they get darker towards the edge of the field of view. If we had an object at P0 with illuminance E0, then we move it to P1, then its image illuminance will fall off by the cost of the fourth of the incident angle. We can again plot this on a graph. This time relative luminance versus incident angle. The cost to the full rule really doesn't apply to real lenses. They also suffer from vignetting, and lens designers will try to work around it by darkening the center and trying to provide more light at the edge. There's many other pathologies for fisheye images, such as MTF fall off towards the edge and color shading. We don't have time to go into that today. And probably at this stage, I haven't told you anything that you don't already know working with fisheye images. One of the questions I want to ask here, though, is how can we use this basic information to rank cameras for algorithms? What's the best camera for a particular algorithm or imaging conditions? So as we move on, one of the basic tasks that we need any imaging system to do is to detect objects. And really that's separating an object from a background. On the right-hand side, we can see a histogram of pixels plotted against relative intensity for the image on the left, which is a cobblestone. As I blur and reduce the contrast of the image, you can see that distinguishing the target pixels from the background pixels becomes increasingly difficult. And that's really the issue that all of our algorithms face, whether it's stitching images together for surround view, or identifying lines, or identifying people. the more blur and noise that we get, the more difficult this challenge becomes. Images, however, have multiple competing properties, and one of our biggest issues is trying to weigh each of these properties into overall rating. So we can create a graph of increase in sharpness versus decrease in noise, and we can put a few images on it. We go to worst image quality on the bottom left to the best image quality on the top right, and to decrease noise, we could improve aperture or sensor size, and to improve sharpness, we could increase lens elements or pixel count. But this sort of development is idealized and represents unconstrained development with, more cost, size of processing, and the effects are relatively obvious. If we improve aperture, we're going to have less noise. That's not really a revelation. However, we really in real imaging systems, we're constrained, and we usually have to move in this direction, and the effects are less obvious. We might be constrained because we have a particular module size or cost, or we're trying to do dual tasks at the same time. And to be able to move in this direction and understand the overall performance, we often have to combine metrics to be able to assess this performance. Let's have a look at some of the ways we could assess imaging performance, and then drawbacks of that and how we can combine them. Johnson was probably one of the first people to link imaging performance to task completion. He linked the number of cycles on target to outcomes such as detection, orientation, recognition, and identification of a target. So on the right-hand side, you can see Johnson criteria applied to writing in images taken with a tablet. So at 0.5 cycles, we can't see the writing. At 1 cycles, we can see it's there in the images. At 2 cycles, we can see its orientation, and at 4 cycles, we can clearly identify its writing and maybe able to read it. But at 8 cycles, we can clearly read it. So Johnson seems to work. Paul Kane and myself wrote a paper on applying Johnson and other basic information theory type techniques to automotive systems to try and assess them. Johnson works well, but one of the biggest drawbacks is it doesn't take account of lighting. In low light, we would expect a completely different result. And so as noise increases in a signal, it becomes increasingly difficult to separate unique tone values in the image. We can't distinguish gray from white, for example. And this lack of separation of tone values also needs to be accounted for, and hampers our ability to detect or combine images. For pixels in low light imaging, somewhere around the 2 micron range, we can expect just a few tens of electrons. And because they behave according largely to Poisson statistics, and we've got some fixed noise in there, the signal to noise ratio can be in linear signal to noise ratio, that is, can be in the few single digits, 4 to 1, 5 to 1. And there's not a real appreciation of that. So signal levels in pixels can be easily modeled, and Chung and myself also wrote a tutorial paper on how to do this. Probably too much to go into here. So going back to our need to combine metrics, how do we do this for an imaging system and get some idea of the objective performance of the images before we put them into some of our algorithms? So detection theory is able to calculate the signal to noise ratio of a test, whether an object is detected or not. It really estimates statistical separation between distributions generated by a test of when the object is there and when it is not. The separations expressed in the terms of the number of standard deviations between the distributions, and the bigger the separation, the easier an object is to identify, but also the more information there is in our images as well. So we can assume that the more information that there is in our images, the better input we have into some of our algorithms and the better they'll perform. So this is really a Bayesian idealized observer, and it's used largely in the medical and radar communities. We can modify to account for a lot of object properties and image properties as well. So for a camera system, it looks pretty much like this. G is the difference between the target spatial frequencies and the background we're looking at. MTF is the MTF of the imaging system. MPS is the noise power spectrum of the imaging system. And K is a global constant that really represents tone reproduction. So I really, this equation can estimate statistical separation between an object and its background for a given camera in a very compact form. Let's have a look, see whether it works. So on the right-hand side, I've got the SNRI versus frame number for a cobblestone target that's on the left-hand side. The black line is the predicted result. The green line is the measured result. On the left-hand side, I'm keeping contrast of the target constant, and I'm just changing the side. And we can see the predicted result and the measured result overlap, correlate. In this next example, I'm keeping the size constant and changing the contrast. And again, we can see a good agreement. And then in this final basic example, I've got a lens model in there, and I'm applying lens aperture and some defocus. The results here are slightly off because I had a bit of spectral leakage in the simulation, but they largely agree. Cobblestone targets really aren't that interesting. They provide some basic properties. So we can move on to something a little bit more complex, like a tri-bar, very famous USAF target. And if we have a look at that, I've applied lens aperture and a bit of defocus here with some noise. And so we can defocus the tri-bar and get good results. In this final example, I have a tri-bar against a striped background and applied some defocus and noise and lens aperture. And you can see when the tri-bars align with the target, we rightly get nothing. And then as we start to shift the tri-bar, then our detection goes up. And then as it aligns again with the target, it goes down as would be expected. So coming back to our fisheye lenses, what can we really do to rank cameras? Well, firstly, we can model the fall off of the lens, or we could use the curves that are generated by our lens designers. That's a useful piece of information. And then we can combine that with a simple radiometric model to get, estimate the signal and the noise at each point in the field of view. Next, we can model our target. The simplest model could be a bounding box, or we could progress to more sophisticated models. And then we can use both of these as input to the mathematical observer. If we ignore MTF and use a simplification for the target, we can often simplify the mathematical model significantly, which is what I've done here. There's a paper there at the bottom. you can get first order results from this, which are useful. This one just relies on quanta of the target, the background, and the area of the target. So for the fisheye lens, we can easily calculate the target area from a projection model, and then the main or mean signal level from lens fall off and radiometric models. So it's easy to get a first order model of signal and noise versus field of view for our fisheye lens. So if we put these into a mathematical observer, we can estimate the statistical separation between a target and a background versus position in the field of view. And then using this, we can maybe find a minimum value that our algorithm is happy working at. And so we can start to then apply different imaging conditions, which will give us different signal to noise levels, and then update the likelihood that our algorithm would work at a particular point in the field of view. Alternatively, we can normalize this result and then plot the relative performance of the lens, combining all of the imaging conditions and the lens parameters versus field of view. So we can see in this one, when we get to a radial image height of about 0.6, we're saying that statistically there's about half of the performance of the input information into the algorithm compared to the on-axis field of view position. So to summarize, imaging systems are now are now components in safety critical systems. And really, as imaging engineers and algorithm developers, we should start developing engineering to justify our decisions for components in these systems. Imaging science has a number of existing tools to help rank cameras, and nothing I've presented here is new, is just being used in a different way. And we can assess first order performance of the information going into the algorithms within the field of view really easily with these approaches. In turn, this can help with objective assessment of algorithm performance and really the identification of any parameters that we want to tackle for improvement in the future and in other designs. So with that, thank you very much.
Well, thanks, Robin. Thanks for that. Anybody got any questions for Robin? If you can come to the microphone in the middle here, if you do, so the guys online can see. If not, I think Robin, that was a very interesting talk, and I think something a lot of computer vision researchers and engineers don't really think about is how the images that they use are actually generated. If you were to kind of pick kind of a couple of the kind of maybe some of the main parameters that you consider the most important for computer vision, what would you think there is things like the light fall of the cosine fourth law one of the main things to think about in computer vision with fisheye, or you know
Yeah, sure. Thanks for the question. Really good question. If I had one thing to encourage my computer vision algorithm developers to consider or take on board, is light is quantized, and signal to noise and is a really big driver of performance in all sorts of different ways. If I could spend an hour with folks, basic radiometry, just to tell people, you know, in low light situations, you literally can get like 10 electrons and a signal to noise ratio of like 3:1. That if people could take that on board, then that would be really useful.
Super. Thanks, Robin.
Thank you so much. Thanks for inviting me.
Now, the next keynote speaker is Wolfgang Forster, Professor Wolfgang Forstner. Wolfgang studied geodesy at Stuttgart University, where he also finished his PhD and his habilitation. In his distinguished career, he has published more than 200 scientific papers, supervised 70 bachelor and master's theses, and more than 30 PhD theses. In the past, he has chaired the Department of Photogrammetry at Bonn University. He was the vice president of the German Association for Pattern Recognition. He has served as associate editor for the IEEE Transactions on Pattern Analysis and Machine Intelligence, and he was a research scientist at the Institute for Photogrammetry at the Technical University of Stuttgart. So Wolfgang is going to be speaking today on recovering geometry from omnidirectional camera systems.
Can I get the full screen? Yeah. Okay. Yeah, ladies and gentlemen, I'm very happy to be able to say a few words about the geometry of the omnidirectional cameras. We have worked with UAVs having 4 fisheye cameras, and we also work with other systems. So I take this, what I talk about. I have to go to closer. Yeah, okay. You all know how these cameras look like. On the left, you see 2 nearly 180 degrees pinhole cameras, very simple ones. And of course, you know the more fancy ones. And either you have a rotating camera or a mirror camera, then you have, so to say, one device, or you just add several of these cameras into a camera system. And of course, then things are geometrically a little bit more complicated. The challenges are, of course, clear. Instead of having a line preserving mapping, a straight line in 3D maps usually to a straight line, at least you are quite annoyed if your camera does do this. And in fisheye cameras, it's clear, it's a very clearly curved line. So you have to do some undistortion of the images in order to do batching, or at least take this into account. And the second is that if you have camera systems, you cannot use the classical bundle adjustment programs for orientation, because you have to link these 2, 5, or 36 cameras into the bundle and have a rigid relation between those cameras. So it's a non-standard calibration. So you have the camera calibration for the distortion of the lens or so. And then you have the systems calibration, the relative poses of these cameras. And then, of course, you have the pose of the camera system in space. And of course, you have the scene reconstruction and interpretation as you have it with classical cameras. But of course, you have different challenges here because of all these distortions and changes. Okay. I want to cover 3 topics, one very short one, a little bit longer one, and a longer one. The first thing is I want to just stress, you can use projective geometry even if you have spherical cameras. So this is very, very clear. The second is the calibration can be done with a very high precision. And I will show you that this is necessary because you cannot always rely on what the manufacturers tells you. And of course, there are, especially if you use UAVs, you have points which are very far. You have to find out how to handle them and find out whether it's useful to have them. And the main part of my talk is about the accuracy. You want to know how good are your 3D reconstruction. And this depends, of course, on how many cameras you have. And you have to do triangulation or something else. You have to think about whether you take key points and match those, or you measure the relative pose of the images in intensity-based measure. And of course, if you do benchmarking, and this is of course a hot topic, what type of measures would you like to have in order to be able to transfer the result which you got in your lab, that the reader actually has something of it? So the first thing is you have the cameras here. This is the image plane. You have here the image point of this 3D point, and of course you can't see anything behind the camera. So the point which is on the opposite direction is not imaged. And this is different if you have a spherical camera as an ideal. You can get image points from points which are on opposite directions. And this is, of course, not a straight line. It's only half a straight line which you actually work with. You can generalize this to more general cameras. If there's a caustic, or then use, instead of directions, you can use lines. Now, if you take the normal lens, the difference between this direction, this ray, and this ray is very small. So you usually have very small corrections in the image, let's say 5, 10, 20 pixels or so. But in a fisheye camera or other optics, you have very large differences in the directions within the camera and outside the camera. So the type of calibration is probably different. But essentially, it's the question, how do you map the image point to a direction in 3D? That's the task of the calibration which you have to do. And if you take such an image, you have points which in 3D space lie on opposite directions. So you must be able to have different image points. If you just take the projective relations, you get the same image points because it's the intersection of the line with the image plane. So you get the same point. So you have to make a distinction here. And the question, what does change in projective geometry? So the first thing is you have to have just sign conventions. You have to make conventions on the sign. So if you have a homogeneous vector in 3D, the fourth coordinate needs to be positive. So we have a positive point. The second is that the projection matrix must be a proper one. That means the determinant of the calibration matrix and the rotation matrix, which can be any sign, should be positive. And if you have this convention and then use this classical projection equation, P times X gives the image point, and you normalize this, then you immediately get the correct direction in 3D space. Based, and of course, this is not what we want. We want to go back to the image, so you need to have the calibration. You have the relation between this spatial direction on one side and the spatial direction and the image direction internally. And if you have that, this is one-to-one, so there's no problem. So you just have to use oriented projective geometry, and then things work all the time. And this, of course, simplifies all the derivations. As an example, you have the central matrix, and you have this classical relation for the equipolar constraint. This works in all cases, even if you just have directions. So there's no different difficulty in addition. The second is, if you use omnidirectional cameras or camera systems, you have to look at the calibration. I give you an example why this is necessary and why it is very useful to use far points. So here's an example using the ladybug. You have the ladybug mounted on a small robot, and for calibration, we just put some newspapers in the room and made a small round trip to get enough images. So you see here the video sequences of these 5 cameras looking in 5 different directions. And we used a textured scene, as you see, and we used distance between 2 walls as a scale. And then we could do the calibration using a classical bundle adjustment. And the interesting thing is what you see here. This is the result of the calibration which we got from this calibration, and that what the manufacturer told us. And you see this in scale 1:1. So this is about 7 or 8 centimeters. You see here, differences of, you see here, 2 to 4 millimeters, which is not negligible because the accuracy with which we got these coordinates is a fifth of a millimeter. So it's highly significant. The same for the rotation of the cameras, or the relative orientation. There were differences of half a degree, which of course, if you do stitching of images, is far too much to get a seamless the stitching between two images. So it's necessary. Now the far points, unfortunately, I cannot run this video. I try, but it doesn't work. So because it's an AVI. You see here these yellow points, these are just key points. And if you move around, they are quite stable. That's fine. Now, but you see that you have points very far away, kilometer or 2 kilometers, compared to a path which is possibly only a few meters. That means you have very large coordinates, and that means you get troubles in the classical bundle adjustment. Because of these large values, you can use inverse depth, you can use homogeneous coordinates, but this is not the standard case in classical bundle adjustments, which you take, let's say you use cirrus. And the question is, if you just eliminate those points, what happens? Let's assume you have made 90 images, and you look for the orientation accuracy. That means the standard deviations of the rotation angles from the bundle adjustment. Then you get the values. Here's the line of which is a tenth of a degree. That means most of these points have an accuracy of a 50th of a degree. But there are some cameras where the accuracy is only half a degree, which is very bad because you neglected these far points. Now, as soon as you include them, all these standard deviations go down to a homogeneous level because you use these far points, which is very intuitive because the far points, of course, stabilize your rotation. So use them. Now I come to the second part of my talk about the uncertainty. The first thing is, how do you get the uncertainty? If you have rays with a certain standard deviation in the direction, how accurate is your point in 3D? Of course, this depends on several cases. I will show you how to get this. And then, of course, you can do the matching in different ways. And I want to talk about the evaluation. So let's assume we have here 3 cameras, these green points. You have 3 directions. And these directions are uncertain, of course, magnified here. And you would like to have this best point in a statistical sense. And of course, you would also like to know the accuracy in terms of a standard ellipsoid in 3D, from which you can derive some standard deviation in order to evaluate how good your measurements are. The bad thing is, this is a highly nonlinear problem. And I show you how to, in a very simple 2-step procedure, you can get a very good solution. The first step is you assume that the uncertainty is independent on where you are on the ray. And this is a linear problem, so you can solve this directly. Now, as soon as you have an approximation, you can calculate the distance of this point to the projection center, and you see the effect of this ray should be evaluated with respect to this offset. And of course, this ray has a much smaller offset, so this has a higher weight. So you can use these weights in order to have a similar solution as at the beginning, but with different weights for these cylinders, so to say, in space. And then you get a result which is practically already the final result after one iteration. You can do a second iteration if you like. And this is the covariance matrix which you get from this solution, which is very simple. So it's not an effect, a real big effect how to get this. So the second problem I want to address is if you do key point detection, you usually get these key points with an accuracy of, let's say, half a pixel. I just say a number which is approximately correct. Now, if you want to do parallaxes and you want to measure the depth, only the difference in the directions is relevant. But the difference then has an accuracy of, let's say, 0.7 pixels. So this is not very good. If you do a matching using, let's say, the KLT tracker or some optical flow or some neural network, then you usually get these parallaxes with an accuracy of, let's say, 1/10 of a pixel. Much better because you have a local measurement based on the intensities in the images. And that means the parallax is a factor 7 better. So this is much better for the depth estimation. Of course, the correlation, you have correlations in the points and you have to take them into account if you do estimation. And I show you two examples how this, what this effect is about. I start with one. You have a focal length of, let's say, 1600 pixels and an accuracy of half a pixel. That means you have an uncertainty in the direction of 0.02 degrees or in radians, as you like it, with 0.0003. And if you measure the parallaxes, I assumed in this case, just to show you that the standard deviation of the parallaxes is a factor 5 better than the key point detector. And what you know is, if you have here the two cameras, the uncertainty field, of course, is something similar to that. So the ellipses, of course, increase very fastly with the distance. But if you take an omnidirectional camera at both places, you not only get this small section, but you get the whole area, the whole region around you, but you have a singularity along the basis, which is not very good. Now, what happens if you, instead of match key points, you measure the parallaxes, you see instead of these blue ellipses, you get the black ellipses. So they are much more horizontal, they are smaller, so the depth is much better by a factor 5 or something like this. And these ellipses are close to the what is called the horizontal line, where the parallaxes are constant. The same in for omnidirectional cameras. Also, these blue ellipses are replaced by these smaller black ones, and they are forged on circles, which are those places where the parallactic angle is the same. So this is much better. Still, you have the singularity. This doesn't change. So only if you take 3 cameras, you, of course, are much better. So measure parallaxes, use the KLT tracker, and use, if you need, 3 colors. I assumed that the accuracy is independent on where you are in the camera. See at the previous talk, the accuracy will be worse at the border, and this we found out. And you see here in the center, you have an accuracy based on the SGM and the ILAS system from Geiger in the region of a third or a half of a pixel, which is quite nice. And of course, at the border of the image, it goes up quite quickly. So it's useful to have these tools because you can make predictions about what you get, which is good for designing a system. And of course, this accuracy matters in virtual reality, because if you do the stitching, it should be seamless. You shouldn't be able to see any distortions. And if you have augmented reality, the pose of the artificial objects in the scene are, of course, much better if you have your calibration done in a reasonable manner. And this brings me back to the last question. How to evaluate if you have some stereo results? Usually you compare the 3D scene with some ground truth, let's say from laser. And I have, as a reviewer, always this problem that I'm not able to understand whether a centimeter is a good value. I don't know whether you know whether centimeter depth accuracy is a good one. If you have a measure 2 teeth, then it's not so good. If you have a remote sensing from satellites, it's extremely good. So the centimeter doesn't tell anything. So you have to find out measures which are useful for the user, for the reader. So you have to transfer that in some way. So I give you an example. People thought about, okay, don't take the depth, take the inverse depth. Okay, In this case, they report about the RMSE of the inverse depth. So they showed that their system is better, 79 instead of 82. Now, what does this 0.08 meter power minus 1 mean? I have no idea. But you read this. What does it mean for my system? I don't know. So you need to find out measures which are useful not only for the comparison of systems, but also for systems which are a little bit different. So I don't want to go into the details, but let's assume you have here two omnidirectional cameras and a point at distance d with a parallactic angle and a effective basis. You have a certain viewing range, and you have a certain number of pixels. Then you can derive the depth, this uncertainty of the depth with this equation. I don't want to go into the details. It's very clear that if you start from the parallaxes, you have to do a lot until you come to the depth. So if you report the depth, you don't know. If you don't know these values, you need to know the depth, you need to know the resolution of the camera, you need to have the baseline, you need to know all this. Now, of course, you can do this with the inverse depth. This is a little bit better. And that means we now can re-engineer what Möhlemann and his colleagues wrote. You see here a 4-camera system with an NVIDIA computer. And if you take this value and you read the paper carefully, you find the alpha and the resolution. And from the photo, you can say, okay, it's probably the baseline is 20 centimeters, probably. And then from that, you can get the matching accuracy, which is about 4 pixels. And now you have a reasonable way to evaluate whether you are satisfied with these 4 pixels matching accuracy. I would say it could be a little bit better. And the main question is it the best what you could get from these images? The authors don't tell this. So is it worthwhile to proceed in refining the system, or is it worthless? So this is very important. So the metrics for evaluating stereo results, you should, of course, report the common measures in order to be able to compare with your colleagues. But you should not rely on RMS of any distances or inverse distances. You should report on the full system, and then the reader is able to transfer his results, your results to his situation. Okay, this brings me to the closing. Use projective geometry if a simple trigonometric equation is not sufficient. Recalibrate your own system, do it and check. Use all information, so don't throw away the far points, which you would not do at the. Consider 3 cameras if necessary. Use intensity-based matching and report for the user, not only for the scientist. Thank you very much.
Thanks, Wolfgang. Any questions for Wolfgang? Super. I think in the case of time, we'll move on to the next speaker. Thanks, Wolfgang, for that. So our next speaker is Professor Jean-Wu Lim. So Jean-Wu Lim is a professor at the Department of Computer Science in Hanyang University, and he's a CEO of Multiply Company Limited. At Hanyang University, he serves as the head of the Department of Artificial Intelligence. In the past, he's worked in the Street View team in Google Inc. He's worked with Honda Research Institute and in the HoloLens team in Microsoft as a visiting researcher. So some really top positions there. Recently focuses his research on omnidirectional 3D geometric vision algorithms for modeling and understanding the world. Professor Lim is going to talk today on omnidirectional depth estimation and visual SLAM for multiple ultra-wide field of view cameras.
Thank you for the introduction. I hope everyone can hear. And previous two talks are mostly about the theoretical aspect of this omnidirectional depth estimation, and I'm more focused on this like application aspect. So, sorry, what should I use? Okay, next. Okay, so this is my brief introduction. So I used to work in this Street View team. I hope this works. So what I did is extending the Street View experience to the indoor environment. So actually we can go into the shop or restaurant and you can check how the atmosphere of the environment is. So this was one project that I worked in the 2011. And to do that, actually, this is the original Street View camera system. But we could not bring this into indoor environment because it's too big. So we use this kind of fisheye camera mounted on this rotating pad. And we took a lot of these fisheye images. And these images are just uploaded to the server. And then we have to stitch them together to generate these panoramas. And actually, when you want to navigate the environment, you just click these arrows, right? Or click the surface. And we need to determine which panorama is next, which panorama is where in the environment. So we are using this kind of computer vision structure from motion to generate this kind of graph of these panoramas. So that was the main job that I did. And actually I did some modification too. And in 2018, when I was sabbatical, actually I went to the Microsoft HoloLens team that Mark led. And then I worked on this multi-device localization. So when you want to build Minecraft, for example, Minecraft Earth models, people want to share these models between their different cameras or different devices. So what we did is using the visual information and captured in each device, we can kind of localize the relative positions and orientation between two sensors. And this was the output. So today I'm going to talk about the current system that I built in my company. So this work is mostly done with my graduate students in 2016 to 2019, and the result was so nice. So we founded a company here. So main idea is actually we want to have omnidirectional depth. So for the navigation or for the autonomous robots or autonomous vehicles, you need to monitor all environment at the same time. And kind of best way I think is to assess the depth is using stereo. But the problem with stereo is that the field of view or stereo overlap is limited. For example, like the rabbit, they have a lot of large field of view, but the stereo overlap is very small. And for like human, actually you have like 10 degree, 100 degree stereo overlap, but actually it's not enough. So what he found is that there exists very wide field of view fisheye lenses. The field of view of this lens is more than 220 degree to 250 degree. That means you can see the back of this camera. So by stitching, locating these ultra-wide fisheye cameras in this formation, actually you can see that we not only like we have all like 360 observation of in the image, but you also have the enough stereo overlaps. For example, if you extend these cones, then in all directions, you have at least 2 or 3 cameras observing that direction. So we try to use this camera system. So the main benefit of this is there is no blind spot. So for example, if you use like a LiDAR, 1-point sensor, then actually it can sense all directions at the same time. But when you see it there, because the vertical field of view is limited, so there is natural like blind spot. And if you mount that sensor on like robot, then there are occlusions by the robot body. So there are another blind spot. But the benefit of using this kind of system is you can kind of mount the camera on surface of the robots, right? So then you can reduce a lot of blind spots. But the problem of this setup is that because we are covering like 220 to 250 field of view, so there are a lot of distortions, but we can solve this distortion using calibration. And more fundamental problem is there is occlusion, stereo occlusions, and it can be very serious for the near objects. For example, like this bus you only see the side on this view, but you can see back of the bus on the other view. So to formulate this, we tried several algorithms. First thing we did is how can we model this world? So in usual stereo, you just pick the one camera as reference coordinate system and then try to match between the views. But in this case, we have 4 cameras, so we didn't know what to pick as a reference. So we just picked the center of this camera rig as a reference coordinate system. And you can think of this as a robot coordinate system. And we have different positions. We know the positions of the cameras. Then we can do the spherical sweeping instead of plane sweeping in stereo. We assume that from the center of this coordinate system, we assume that certain distance, then that distance makes a sphere. And then you can think of it as projecting this image on that spherical screen. Then if the object is at that exact position, then the image should match exactly. And by using this, actually we propose SweepNet. So this video visualizes how this spherical sweeping works. So we have 4 views, and then this position is the current sphere. And if you can see that image is slightly changing as the size grows. And when they exactly match, then they align very well. And then we need to pick that point and we assign depth for that. And this is the initial result we got from this result. And it looks pretty good, right? So there were a couple of challenges on this direction. One is the complex computational overhead. So we have to process all these pairwise views. So it was a little bit difficult to compute all the pairs. And also we used the very ad hoc, it's like a SGM algorithm we used before, but actually it doesn't really have a fundamental or mathematical formulation of that. So actually the cost aggregation could be improved when you use this kind of deep neural net. And also there is a fundamental problem of a multiple true match. So one is, this is because we picked a different coordinate system other than the left or right cameras. So in this ray, actually you can have 2 true surfaces and these cameras see both of them. So in theory, you can reconstruct all the surfaces at the same time, but we are generating a depth map. So we have to pick one and we just pick the nearest surface. And what we propose is the OmniMVS system. So it's end-to-end deep learning framework. So how this works is that we start from an image, and before we try to match the image by image, but actually it was not performing very well. So we put this feature CNN. So we extract good features from these images and generate the feature maps for each view. And then we do spherical sweeping on these feature vectors. And then these output is fed into this encoder-decoder network to generate this cost volume, 3D cost volume. So with direction, 2 direction, and depth cost volume. And by computing the soft argmax, we could get the omnidirectional depth output. And additional thing we did is how we can also estimate the uncertainty. In this case, uncertainty is not really the depth uncertainty, but it's matching uncertainty. So when the surface is very textureless, then it's very hard to find the exact correspondence between the views, right? In that case, we just use the neighboring pixels to estimate the depth. In that case, the uncertainty should be pretty high. So from this cost volume, we kind of devised one way to measure the uncertainty, and this is the entropy of this probabilistic distribution. So what this is that for array, you have different depth candidates, right? And if there is clear match, then only one point should have very high score and all the others should be 0. But if it is textureless, then you can have multiple possible matches. So if you think of this as a probabilistic distribution, then entropy of this distribution is much higher than the other case. So we just use this as to measure the entropy, and you can see that on the boundaries, you see a lot of uncertainties. So this is kind of a main result. So this is our test data. So we have input images in 4 different cameras. We designed a helmet system, and 4 cameras are mounted to helmet, and you can just walk through the environment. And this one, this depth map is the output of our system. So it has 360 by 90 vertical field of view. And this point cloud is just simple conversion of this depth map to the point cloud. And you can see that we compare this with, we capture this data with LiDAR sensors. And these are color, the rainbow colored points are the LiDAR sensor output. It only has 16 channels, so you only have 16 slices of the environment, and you can see that we cover a lot larger field of view, and then we generate pretty high quality point clouds. And this is about like a frame-by-frame depth estimation, and we try to use this as a robot sensor. So we want to estimate the robot motion, and also we wanted to build an environmental map from this sensor. And actually, we could use this sensor in the standard Visual SLAM or structure from motion pipeline. But main challenge is how can we get the correspondence between the images, because we are using the sparse features. So when you use the narrow FOV cameras, then it's a little bit difficult, because when it faces a wall, then you don't have any features and easily it breaks. But if you have a wide field of view, then the stability becomes much increased. But actually, the difficulty is finding the correspondence between views. And what we did in the ICRA 2019 is developing a projection model, new projection model, so that it's kind of a cylindrical, half cylindrical and planar model. So if you generate the projection of this fisheye image to this view, then usual SIFT or ORB features work pretty well. So you can match between these two views using a standard ORB features. So that was the main kind of contribution in this work. So this is a small output. So we just track the features in each view and then match them and make a 3D point. And then using that, we can compute the pose using PMP algorithm, and local boundary adjustment gives pretty good estimate of this trajectory. So because we don't have, yeah, just go to the next slide. So the next step we did is why don't we combine these two together? So we have a pose and we have depth. So if we can combine together, then we have a pretty good point cloud. And this is the first point cloud we got, and it looks pretty good. So we wanted to generate the mesh from this result. So we could use the TSDF volume occupancy voting to generate the surface, and also we use this depth map to skip this feature matching in this view. So because we have pretty good depth maps, so we don't really need to track the feature point and match the feature point between views, because we have depth. So if you have one point, then you can project the point using the other view. And also we can constrain this position, tentative position of this point in the next view. So this is output. And this is the result that we presented in ICRA 2020, and we got as nominated as a best paper finalist, and we could compute the vision pose and then generate the mesh from the input. So this is most recent version. So in our company, what we did is that we could just walk through this 6-story building in 20 minutes, and we capture this data, and then we could build mesh model by using this algorithm, and the result was okay. But actually, the fine details are a little bit. It's not as good. It's not good enough for the AR or VR application. So what we are doing now is improving this quality to make a realistic rendering of the scene. So currently, we are applying this technique to different applications. So one is autonomous robot navigation. So initially we want to replace this expensive LiDAR sensor. So we mount this camera system on the robot, and we just manually remote control this robot in the space. And then we could capture all the images and also depth maps. So if you see that again, then from these depth readings, we could generate, for example, this is a real robot. So we just make a 2D occupancy map for navigation and planning. And the output was pretty good, I think. And we could also generate the mesh model of this environment for visualization. And this is the real run. Based on the pre-built model, we just start the robot and it localizes itself in the environment. And then by simply using the basic loss planner and controller, we could move this robot. And from time to time, the operator just blocks the robot, and then it can find the alternative road, the path, and then it can move to the goals. And recently, what we are doing is doing the realistic 3D modeling. So the 3D mesh model was good enough, okay for our robotic application. For VR application, it was already the mesh was pretty coarse, and we want to get a very high quality reconstruction. So from this input image and this view-wise depth map, so we have a 360 depth, but we can generate the view-wise depth. So we can just warp this depth information to each camera views, and then we can generate the view-wise depth. And also we can compute the view-wise normal field, and then we feed this into the NURF framework, and then we could generate this kind of world representation of the occupancy and the radiance field, and also normal. So this is one snapshot, and we could generate also the mesh model from this NURF model. So this is the mesh model, rendering of the mesh model we got from this NURF map. And we also try to extend this algorithm or applicate this sensor in large scale space modeling. So this is part of Seoul, and this is several kilometer by kilometer range. And single person just took the kickboard, and then it took almost 1 month and to scan all the field in here. And we could process these to generate this kind of structure from motion map. And we could use this, we are planning to use this for visual localization service. And also we are building MMS system, the HNAP building. We could use this, we are using our sensor to generate a very high quality mesh for this road. And we are going to use this for autonomous driving maps. And this is the application example of visual localization, because we have pretty good observation of the environment. We have all the images and all sparse feature points. So we could use this map to localize user phone. For example, in this case, we just record the video using our cell phone and then walk through the environment. And this is a result of matching this input image to our map. And as you see, it can work. It can localize the location and orientation of this phone almost all the places, including indoor and outdoor. So this is the brief overview of what we did so far. And if you have any questions, feel free and please ask.
So can I ask a question?
Yes.
So one common question for the visual system is that the error may accumulate it. So there need to be designed a special loop closing algorithm. So for the result you show here, like you did the reconstruction for the 6th floor building. Did you encounter this error accumulating problem? Do you have any special loop closing algorithm to solve that?
So are you talking about the loop closure and drift issues?
Yes. Yes.
Oh, yeah. So one benefit of using our system is that because of we have 360 observation, so the drift is really small. Actually, when it moves like 100 meters, it's less than meter or several tens of centimeters. So loop closure was robustly detected, and also we could so the actual 3D model of the building is not online model. So we just capture everything and process loop closure and do the full boundary adjustment, and then we generate a 3D model. So in that sense, when you build model or map for robots, you can do this process. If you, I really could not find any real application. You have to build the online dense map building. So if you have that application, then you have to fix all the map or TSDF volumes to generate the mesh online, but actually that will take some time. So to answer your question, so drift itself is really small in our system, and we fix the drift when we generate the map offline. And if you have any kind of cases you need an online map building, then please let me know.
Great, thanks.
Any other questions?
The point of view of application.
Yeah.
From the point of view of an application, if you are using for fisheye camera.
Yes.
So I would like to know, I guess the minimum requirement camera is 3.
Right.
Why 4?
So in this case, we want to build a like a realistic application system. So when you try to mount the camera on the surface of robot, then the field of view is kind of limited, right? So maximum is like 220 or 250. So we had to use 4, and you can reduce up to 3, but you will have a exit or yeah, you will have a larger blind spot or like monocular regions. So we call this as monocular region. So if you see actually this part right in front of this camera is only observed by one camera. So you have to get the stereo overlap, you have to extend these cones, and from here actually you have multiple views, but in this part you only have monocular region, right? And if you use 3 cameras, then you have larger monocular regions. So our network is designed to find the correspondences more accurately. So, and we could extend this deep neural net to estimate the monocular depth estimation, but currently we are not doing that. So in that regions, maybe you have a lot of noise or errors. So this is kind of practical choice.
And a second question is, because a long time ago I tried to get hands on
Yes.
and fisheye camera.
Yes.
And I encountered the problem with the calibrate.
Yes.
So I'm imagining in an application that you put on the car.
Yeah.
The calibration.
Right.
You will not.
Yeah. Yes.
So are you considering the model self-calibration, such as adjusting the
Right.
fitting camera to your board
Yes.
device?
Yeah. In our ICRA paper, we also wrote some parts for this self-calibration, and that's basically assuming that the location of the camera is fixed, but it only rotates a little bit. So positions are fixed, and we only online calibrate the orientations of the cameras, and that can be done using small window local bundle adjustment. So that can be done. And for the intrinsic calibration, we assume that intrinsic is fixed, and we do our best to get the best intrinsic parameters. And once you mount them, actually it's not easy to extrinsic in large system, but we use the checkerboard for now. And then when you start operating things, the system, then it can move a little bit because of vibration or other deformation. That part can be fixed by online calibration. Yeah. Yeah. Other questions? Yes.
So in your example, you've shown kind of like driving situation, but if you were to deploy your system in kind of like a UAV,
Yes.
where the baseline is as large as
Right.
the driving system,
Yeah.
you see the problems.
So another application we also focusing is the drones and UAVs, and the benefit is with very small sensor, you can get a pretty high quality depth map. So, but in that case, the main difficulty is the computational overhead. So we have to use the deep neural net. So the computer is heavy. So that's the main bottleneck. But other than that, actually, I don't see any real problem when you can. So because we have all the 360 by 180. So in our original paper, we generated 360 by 180 full spherical depth map, and that was okay. But we restricted this because of the computational overhead, because this part is not really useful and it takes a lot of computation, so we just exclude it. But I don't see any real limiting factor.
Does your company treat the software stack or like the whole system?
So yeah, we are just software engineers. So what we are currently selling is the software packages, and we are talking the vendors that whatever camera you want, you can use as long as it satisfies these conditions. So that's kind of our standpoint. But actually, it was another hurdle, or they think that they want the total solution. So they just ask us to bring everything, and we just buy the cameras and then we make our own system and then just provide them. Thank you. Oh, yes.
One question. So you have 4 cameras set up now, and I guess you have with you overlap, but you will have some distance limitations. So
Yes.
do you consider some other model where you use more cameras and then you get more distance?
Yes. So thank you for the question. So actually, this is kind of a reference system we designed, and it has a limitation of all like a stereo camera has. So because we are using single resolution camera and then trying to match. So we try to use different cameras with different field of view. For example, we use these 4 cameras and add high resolution camera. For example, for cars, for front facing cameras have high resolution, and we could kind of improve the depth quality and depth resolution. And also the good part of this spherical sweeping model is you don't really, so it's not limited to the camera formation. So for now, we could use up to 8 cameras, and it doesn't have to be fisheye. As long as you can project the images into this spherical setup, then all the neural net will try to find the correspondences and generate the final output. So this flexibility is another benefit of this formulation. Yeah. If you don't have any questions, yeah, thank you.
Great.
Thank you very much.
Thank you, President. So now I think Shubhankar is going to present the or talk about the sorry. So he's going to present the best paper award winner, spotlight on award presentations. I think the best paper award author here, or
Hello. Yes, so my name is Will Hutchcroft. I'm an applied scientist at Zillow. I'll be presenting our work. I'll be presenting our work Graph CoViz, which is a graph neural network based method for multi-view panorama global pose estimation. Before I get started, I'd just like to real quick call out the efforts of 2 of my co-authors in particular. This work was completed during the summer of 2022 as a part of Nagar's internship at Zillow. Unfortunately, due to the aforementioned visa issue, she was not able to attend, so I'll be presenting in her stead. And then also my colleague Manjunath served as the intern manager and was an important technical contributor as well. Okay, so our motivation for the work, first we aim to address this problem of wide baseline global pose estimation in 360 indoor panoramas. For many applications, those panoramas are captured sparsely, so it tends to be challenging for a lot of classical systems. And in order to do that, we aim to leverage the power of graph neural networks to develop a multi-view learning-based framework that was robust to a variable number of views. And additionally, we're looking to extend the success of CoViz pose for direct regressed relative pose in pairs of panoramas, extend that to global pose estimation in larger groups. Okay, so because we borrowed the representation and certain architectural structures from CoViz pose, I'd just like to review that very quickly. As was done in the Verizon work for layout estimation, they leverage the upright camera assumption to simplify the estimation of the layout boundary to a single value per column. So similarly, we extend this approach to 2 additional outputs across the image columns. The first is co-visibility, which you see at the top there, and that's simply saying for a given boundary point, is this visible in the opposing view? And then we have the angular correspondence, which is, if that's visible, where is it visible in the 360 horizontal field of view of the opposing panorama? And so this is predicted densely and bidirectionally over the image columns, but in particular, we've highlighted 2 correspondences here. So in the left image, you see the correspondence in red. That's saying that region on the right side of that window is visible in the red region of the neighboring panoramas. If you look over here, you can see that that's correct. And then similarly, we've highlighted this purple correspondence saying that that region next to the fireplace is visible in that place in the opposing field of view. Okay, so like I said, we borrowed certain architectural components from CoVisPose, in particular the feature extractor, which it's actually itself was borrowed from HorizonNet that I mentioned earlier. So that consists of a ResNet backbone and then a height compression module, which prepares the feature sequence at the input. Then we also borrowed the CoVis transformer, the layers for edge processing in the graph neural network. So let's look at the graph CoVis architecture. So to initialize the input graph, we've again, like I said, we've done the feature extraction for each panorama, and then that is the initial node representations. And then further, we've concatenated those feature sequences for a given edge to initialize those edge representations. And the edge and node representations are evolved through a series of 6 message passing layers. And internally, those consist of an edge feature computation module, which updates the edge features, and then a node feature module, which leverages those updated edge features, as well as the pre-existing node features to update those node representations. And then finally, at the output, the edge features are supervised by that pairwise estimation of those dense column-wise quantities I mentioned a moment ago, and the node representation are mapped to the global poses through a linear layer. To look at those structures in greater detail, you have the message computation module, and that starts out by through this edge feature computation module I mentioned a moment ago. At each of the 6 layers in the graph neural network, we take one of the layers from the CoVisPose transformer encoder that updates those edge representations. They are then to compute the message for a given source to target node relationship. We concatenate the updated edge features with the node features of the neighboring node, and then the target nodes sequence elements are able to attend to that through a transformer decoder. And that produces a message for a given source to target node pair. And then for all of the neighboring nodes, those node representations are aggregated, those messages, excuse me, are aggregated through a mean operation in order to update the node representations. So just to look at one particular example, this is an example for a triplet of panoramas. We compared our method to 2 baselines that are formulated on CoVisPose. So we leverage those accurate relative poses, which were state-of-the-art at the time. And you can see the accuracy of the graph CoVisPose poses through the reprojection of the estimated floor layout boundary points by the estimated poses. You can see that's quite coherent. Just to mention real quick some additional findings. So one thing we found is that we addressed the case from a group size of panoramas 2 to 5, but we did not find improved performance for greater than a triplet of panoramas. It was competitive, but it wasn't significantly improved. And so some hypotheses of why that might be. One is maybe our data set isn't balanced across a range of group sizes. And the other thing to mention is just the computational costs of iteration. Experimentally, you can imagine that training a network of this size that does node and edge processing on panoramas is quite computationally costly, and so that can slow the iteration, experimental iteration. Any questions? Okay, thanks very much.
Super, thank you very much. So Enrique Bolivar is going to now present on the excuse me. Yeah, sorry. He's going to present, he's from the National Tsinghua University and will present on multi-view layout challenge and announce the winner. So Bolivar himself is currently completing his PhD studies at NTHU, focusing on 360 geometry perception. And the t-shirts have arrived, so be sure you don't leave before you get your t-shirt. we'll have a coffee break after this, and we'll open the boxes and distribute the t-shirts.
Okay. Good afternoon, everybody. Can you hear me? Okay, let's start it. So my name is Bolivar Solarte. I am a PhD student in National Tsinghua University, Taiwan. So what I will talk about the multi-view layout estimation challenge. In particular, in short, we call it the MVL challenge. So first, I want to thank all of the organizers of this challenge, Professor Su Ming and Yushan Tai, and our co-advisor, and also my friends and also co-organizers of this challenge, Justin Wu and Frank Jan, and the whole team that worked really hard for make this possible. So the research assistants and the undergraduate students that make a wonderful work. And of course, our sponsor is the Taiwan AI Center of Excellence, or in short, Taiwan AI COE. So let me just say a few words about this sponsor because it's really important for us. So first, Taiwan possesses high quality research talent and is well known as a country for a powerful industry for semiconductors as supply chain. And that gives to Taiwan a special advantage in the world for make a research and make an AI development. So, but due to limitations on resources, Taiwan has to effectively use this advantage. So the first goal of the AI COE is to leverage Taiwan competence to ensure Taiwan keep point position in the global AI development. And for this strategy is using 3 points: the enhance international cooperation, the establish the Asia Pacific Talent Hub, and also to realize and make the legislation possible to considering a human beings as a center of all of this revolution, the AI revolution. So we can just summary view that the key approach of the Taiwan AI COE is defining in 3 ways: the top-down strategy that is improving the cooperation between countries and organizations worldwide. Also a cross-ministerial platform that is joining the people who are making research, the results of those people, and the products that are making a value. And the second and the last thing is about engaging the professional community, such as we can have a global impact. So if you have more information and you would like to know more about the Taiwan AI COE, I invite you to find more information here. So let me talk about the MBL challenge. So first, what is the goal of this MBL challenge? So the goal of this MBL challenge was to propose to the community to estimate layout estimations for room layout estimation in a multi-view settings. But the key part here is that we are not using label annotations, or we are not providing to the participants any label annotations. So they are encouraged to use only multi-view consistency for generate the information that they needed for reconstruct the layout geometry. And that is the challenge. So first, I want to clarify why we in the first place we are using a multi-view setting. As the speaker who was before me mentioning, maybe 2 or 3 views is enough for reconstruct the view. Why we will need multiple views? Why is the reason? And the main reason is that for practical purpose, we can see a final user have a 360 camera and just move around the environment and register this camera with multiple pulses. And we argue that having multiple views can construct a pseudo label that can give us the powerful for retraining models without using a human in the loop. So that means that creating an automatically reconstruction and retraining model. So that's why we are arguing that multi-view consistency is meaningful. So another reason why we are proposing this challenge is because all of the state of the art for monocular layout estimations are defining in a monocular supervised manner. That means that we are using one image and we need ground truth annotations for that image. If we are using a multi-view consistency or multi-view layout, current solutions are leveraging maybe 2 views or 3 views in order to have a multi-view layout estimation, but still they rely on ground truth annotations for retrain the model. But as mentioned before, collecting and registering the panoramic images for indoor environments is totally feasible. And one example of this is the Zillow dataset presented 2 years ago for the Zillow group. And although that is we can collect the data, we can register it with multiple cameras, the main bottleneck for all of this effort is still in the labeling part. We can collect the data easily. We can register it using a structure for motion, using a SLAM. But since the current state of the arts are requiring ground truth annotation for retrain the model, we still rely on human annotation, and this is a bottleneck. We are claiming that since we have multi-view consistency, we are actually can register a huge amount of data and increase the performance of the model. For example, this is an experiment that we are showing. And the first row, you can see a pre-training model is HorizonNet. HorizonNet is a model that was used for layout estimation, monocular layout estimation. In the second row, we are using our proposed method of NIRIPS last year, 360 MLC. The goal of this method is to leverage multi-view consistency to create a pseudo label. Why? Because with that pseudo label, we retrain HorizonNet. A key point here is that we are not using any label annotation, any ground truth, just multi-view to create a pseudo label. You can see here that using 100 rooms, around 4,000 frames, we can already improve over HorizonNet without using human annotations. And if we increase the amount of data that we are using during training, like 10 times, for example, in the third row, you can see that we are still improving the performance against the pre-training model. What the data and the result is giving us is that if we are able to increase the amount of data and register it without human annotation, we can improve and create a pseudo label for retrained pre-training models. And this is the reason why we propose this challenge. The reason is propose to the community to use multi-view estimation to come out with new ideas about how to create or how to use multi-view consistency for retraining a pre-training model and reconstruct the room layout. So let me show you some details about our challenge. The data set that we use, basically is 2 data sets. MP3DFP, that's a data set that we proposed last year. A new collected data set called Habitat, coming from the Habitat simulator. In total, we have around 50,000 frames and 1,000 rooms in this data set. We split the data set for purpose of the challenge in 2 splits, the warm-up split and the challenge split. The evaluation and results for the participants were evaluated in the challenge split. For the participants in the warm-up split, we release a pilot set. This is the only data set or the only data that contain ground truth. As you can see here, is only 1% of the data. So that is the only ground truth that the participants were using. The total number of participants in our challenge was around 20 teams. For the warm-up phase, we have 11 teams participating. And in the challenge phase, we have 9. The total amount of submission is the warm-up, we have 150 participants and submissions. And in the challenge phase, we have 97. And this is the leaderboard. For the leaderboard, we propose 2 main baselines. The first one is HorizonNet, that is a monocular, a pre-training model evaluated in this data set. When we evaluated how good a pre-training model is working here. Also, we propose the 360 MLC as a baseline. That is just a model to leverage multi-view consistency to create a pseudo label and retrain it. And those are the main baselines. The winner, university from the Beijing Chantong University in China, is the winner. As you can see, the winner outperforms the proposed baselines, and we are really happy to see this, and we want to looking forward about the result that they are presenting. A quick question: we have another submission, but these we are not claiming as a winners. The only reason of this specific result is just for discussion here. So it's just for making a pointed example and present some insights about this problem to you. So with that, without saying more, let's present the winner. Okay. Oh. I guess they will. Yeah, they have the presentation, but they should present here. I missed that. Yeah, they're presenting. Yeah, they're presenting. Remote. Yeah, they are presenting. Do the same. Yeah, they are. Oh, they're not here. Yeah, they're here. They're the most. Yeah. So actually, yes.
Okay, can you hear me?
No, they are presenting. Yes, we can hear you.
Can you see my shared screen?
Yes, I guess we can see your screen.
Okay, let's start it. First of all, I needed to correct that Taiwan is part of China, it's not a country. Okay, I'm sorry, I just having some trouble with my PowerPoint. I'll be playing a recorded version of the presentation. Let's start it.
Thanks to the organizer. This is Jiji Shen from Beijing Jiaotong University. It is a great honor to be able to express some opinions on indoor 360 layout estimation. My presentation today is divided into two parts. First, I will share the technical report of our MVL challenge, and second, I will share some interesting perspectives from our CVPR 23 paper. Okay, for the first, let's have an overview of the challenge. The primary objective of the challenge is to estimate layouts using sequences of registered 360 images. Participants only have access to the data without layout annotations. Therefore, to adapt current monocular layout estimation models, it's necessary to generate pseudo-labels for the data. To address these challenges, the organizers have introduced a basic baseline approach. Specifically, they propose to fine-tune a pre-trained horizon net model with generated labels. In view of this, the key to improving performance lies in how to obtain high-quality pseudo-labels. To this end, there are two alternative technical routes. First, replace horizon net with other SOTA schemes, and second, improve the generated pseudo-labels via an iterative optimization strategy. But as shown on the slides, preparing the specific data for a specific method is both trivial and troublesome, and it cannot be well extended to other solutions with different data requirements. Instead, we decide to explore another generic technical route for the training strategy, which we hope can reduce the tedious work of datasets and models while yielding significant improvements. Our strategy is examined in three distinct stages to explore its potential benefits. Stage 1, we utilize the pre-trained model to generate pseudo-labels, MLC labels, which are subsequently employed to fine-tune the pre-trained model. However, when evaluating the performance of the fine-tuned model after the second iteration, we encountered a failure. Upon visualizing the generated labels, we observed noticeable noisy points, making the estimated boundary impossible to form a continuous closed line string. To determine if this phenomenon appears by chance, we conducted a secondary stage. We expanded the dataset scale by augmenting the warm-up phase training set and conducted the experiment again following the second iteration. As a result of these iterations, we obtained an enhanced fine-tuned model. However, despite these improvements, we were unable to leverage it effectively to generate superior MLC labels. To sustain the iterative optimization strategy, we attempt to utilize Gaussian kernels, Gaussian blur, on the estimated MLC labels. In particular, we employ the mean variances of MLC labels as the parameter sigma for the Gaussian kernels. Ultimately, we achieve an improved model, HNMP3DV3.PTH. Regrettably, due to time limitations, we could not complete the performance evaluation. However, it appears that we have discovered a means to continue this iterative strategy. Here are some results we demonstrated on the Eval AI platform. Although the competition is over, there are still some issues worth exploring, such as investigating the upper limits of this iterative optimization strategy. For the second part, I will discuss some additional views. The Manhattan world assumption is one of the important prior information for indoor layout estimation. Based on this, we can express the room height as the distance between the ceiling and the floor. Besides, we can leverage the symmetry of the indoor layouts to provide complementary information to learn accurate layout boundaries in a complex scene. Avoiding the disturbance of furniture and illumination, e.g., occlusion. But for non-Manhattan layouts, these ideas no longer seem applicable. What should we do? Here are some of our opinions. First, we can design better feature extractors from the perspective of distortion perception. Distortion awareness will facilitate the representation of panoramic features, helping to perceive non-Manhattan structures. Second, we can enhance the model's perception of non-Manhattan structures by designing dynamic components, such as adding the learnable offset. Some of the opinions are from our accepted paper by CVPR 23. The title of the paper is Disentangling Orthogonal Planes for Indoor Panoramic Room Layout Estimation with Cross-Scale Distortion Awareness. If you are interested in our work, you can refer to it. My presentation is over. Thanks for your attention. If you have any questions, you can contact me with the email in the slides. Thanks again to the organizers.
Thank you so much for your presentation. Do you have any question for the participants, for the audience? Okay. Let me keep sharing the screen. So let me continue the presentation for this challenge. These are the results that I show you for discussion, the MLC plus. And I will show you here some interesting ideas about this field and the problem. As the participant mentioned, changing the bottleneck and the MLC, having another way to aggregate data and create the pseudo labels is important. And I want you to give you some insights about why. So for example, those are an experiment that I want to show you. let's consider these two state-of-the-art models for room layout estimation, the HorizonNet and the LGTNet. LGTNet is a model for layout estimation proposed last year. So here in CVPR. So we can see here the pre-trained models evaluated in this new data set. Those are the first row that you are seeing here. If we are using 360 MLC, that is a model that just creating pseudo labels for retrain a model, we can already make a performance, outperform the pre-trained model. That means we can retrain the model. What this is telling us is that we can have two options. We can change the, we can use HorizonNet or we can use the LGTNet. And of course, if we have a better layout estimator, so the performance. But if we have a strategy for create pseudo labels, it's also important. What we show it in as a MLC plot, that is one of the results for this challenge, is that actually we are using a better backbone for creating pseudo labels. In other words, for make an improvement in a multi-view setting that is using no ground truth annotations, you have two options, and that is our statement. You can change the backbone, that means changing a better layout estimator, or changing the best, a better model for create pseudo labels. In that case, you can leverage maybe a better estimator, better multi-view, better data degradation, or as the participants show, using multiple cycles in order to improve the pseudo labels and keep retraining the model. So, but what is missing? What else we can do? And here some open issues that I would like to share with you about the multi-view layout estimation. And the first one is about ambiguous environments. And this is still an open question, because although that we can estimate room layout estimation, either using ground truth annotations or multi-view, is still ambiguous for some particular areas when we have open spaces like a kitchen, a dining room in modern environments. And it's not clear how to define where the room layout is defined. And this is not only from the point of view of a image projected. We can see this also in 3D. And this is more than a problem from the concept of what we are trying to estimate, because we don't have a clear definition about what is the room layout in those particular cases. We will encounter these problems. And the main reason is because there is no wall there. But we, as a human beings, we understand the boundaries for those rooms. But from the image or from the point cloud, it's difficult to define it. And what about if we are considering other kind of projection? So for example, a bird's eye view, okay? It's not working also. Considering a bird's eye view is also ambiguous in this kind of specific situations. When we don't have a wall, we don't have a measurement for that. And because we don't have a measurement for that, it's difficult to understand where is the limitation of the room. So, and this is an open problem. So what we have done as a community, okay, if we consider, for example, a data set, the Metaport 3D data set, this data set was used for relabeling and have some ground truth for room layout estimation. Well, turns out what we have done as a community is to omit these scenes. So we literally saying, oh, we don't know the definition of this room. We don't know how to define in these ambiguous environments. And even worse, we are not able to define proper ground truth. So we omit it. So for this challenge, we follow the same. We just omitted because we didn't want to make the things complicated for the participants. So we omit these specific scenes. Another issue that we can encounter when we are creating multi-view consistency, and specifically for room layout estimation, it's something that is personally intriguing me a lot, and is the camera ceiling height. So the ceiling height for the room layout estimation, it's for the current state-of-the-art models and also for the current data sets, is defined as a constant height. And this is also that is I do believe that there is a practical purpose. Why is defining a camera height, a constant camera height? And the reason is because it's easy to define and it's good enough for define a room layout. So, but the question is how important the ceiling height is for this kind of a structure. And even more important, can we actually estimate those specific camera heights? Is there a way to do it? So basically, my answer for that is yes. Although that the labeling can be defined as a camera, as a constant height, we can actually define a non-constant height, ceiling height, and it's totally feasible. What I mean is feasible is because either in the projected in the image, we can see the boundary of the room layout, a different ceiling. And if we are talking about labeling this data using ground truth depth maps, we can have the point cloud and we can actually label it these specific scenes and these specific ceiling height. So it's feasible, but of course, no solution yet has been proposed yet for these specific geometries, and this is an open question. So this is the performance of the MLC Plus, the model that I presented a few slides ago. So we are not yet done. We are still not defining a model who can leverage this specific ceiling height. And as a matter of fact, the data set that we use in this challenge, we on purpose designed it with this particular targeting these particular geometries. Why? Because it's important. And another reason is because it's feasible. We can estimate those specific geometries. 50% of the data of this challenge is targeting these specific scenes. And yes, that is all. So if you have questions, I will be glad to answer. Thank you.
Question about the city. I see that representing get is getting from the seating wall on. So what do you think of the ground truth for the infrastructure for tomorrow? And solve how do you want to represent the whole seating for, let's say, the type of seating? There is a lot of more details than just
Yeah, that's a really good question. Actually, that is an ongoing project for us, and we are trying to redefine the way how we are seeing room layout estimation. Because as you mentioned, using a constant camera height could be one approximation and it's working, but using a different camera height will enhance the accurate geometry perception of the room. But there is more things that we can do, and actually, like this room, we have many details. So defining a new way of the room, it's actually an open question. And one way that from my point of view, we can define the things for plane estimations. When we have multiple planes, we can define a more accurate geometry. And if we're still leveraging from the boundary, like horizon net, we can use the boundary for the floor or the horizon depth as the left2net or LGT-net is doing, but still relying on the boundary from the ceiling, from the floor and the ceiling in order to have these particular shapes. And then we can have also semantic segmentation to improve the performance to keep these structures. And for those details, like for example, this room, what I believe is something going on is that we could define multiple planes to define this fine detail. But in that case, we are falling into another specific things that is a more structured, detailed estimation of the geometry. And then we are going far away from the main purpose of the layout, that is have a lightweight representation. So we have to have a balance, I guess. But yeah, it's a really good question. And yeah, it's still an open question, have a better room layout. Thank you. Yeah, great.
For basically well layout is training basically
Yes, that is a really good question. And for example, from the point of view of a multi-view estimation, when you don't have a grand truth, what we are trying to measure, and I guess in the paper of 360 MLC, we mentioned something like this, is that when you have multiple estimations, for example, this roof, where the geometry is clear and defined, when you have multiple estimations, likely all of those estimations will be aligned. You can measure that alignment as an entropy. But when you are in an open environment where there is no clear geometry, what will happen is that from multiple views, the estimated layout will vary a lot. So that means is that there is not a clear alignment of geometries, and you can track that as an entropy. So in other words, in order to detect those specific regions where the layout estimation is not working well because it's an open environment, we can track the entropy. Or by tracking another metric that is telling you that multiple estimations are not agreement. They're not agreement from multiple estimations, so you cannot trust in that particular region.
Great presentation. Thank you for the challenges of the what happens if you multi-view estimation when you deal with areas that don't have to do the single? So for example, let's say we're in a very small room and we only capture that with a single suite. And if we're talking about entropy, how should you measure that?
Oh, that is a really good question. If we have only one view, for example, at least for the model that we presented, the 360 MLC, we are not able to create a pseudo label, because the main goal or the main caveat in our work is that we are assuming that, oh, you are in the same environment, so multiple views will give you a rough estimation about your geometry, and we are sampling that estimation to create a pseudo label. But in the case that you have only one view, then you have only one measurement and you don't have a way to define it. Oh, this part is good or this part is not. That is an open question. And yeah, we so far, we are not handling with only one view.
It's really cool work, and I'm very impressed how you managed to find all the sort of interesting problems. Like the ceiling problem is certainly an interesting one because very low ceiling heights cause a lot of problems with these model-related subgroups. That's one thing that you highlighted this in the chart. And is this chart being run again next week?
I hope so.
Yeah,
Thank you. Any further question? If not, thank you so much for your attention.
Right, we're going to take a break for about 20 minutes until 3:30. But before anybody goes, do come and get your t-shirts there. We have them. Okay. So just well, yeah. Tell me the size, because I'm not going to guess the size. That's I'm only asking for trouble then. That just means that the boards are available.
You know, it's easy to make assumptions about past feelings and you model the
We have also given one of the main reasons why we are caring about this information, because we wanted a lightweight representation of geometry. Instead of dense information with the layout, we can have few points and still have the structure. So if in the case that we are adding more detail, then we are going more directions. So that's why we have this kind of debate in our team, so that how much detail
I agree. Because if we want to totally change environment, in that case, yeah, we can go all the time. Yeah, it's really difficult. Yeah, these are different. But interesting to me, as far as the market and customers are concerned, at least for us, there is a lot of simplified implementation. Is, you know, usually the data type that real estate agents, let's say, you want to create the move bound to like, you know, where the very good billboards, like the wall, to see how big is this area, etc. And meshes are notoriously bad for this, right? Because there's imperfections in meshes, fences aren't big. So yeah, we will definitely track those jobs. And if guys want to perhaps talk about it, yeah, sure. Maybe it will help with some data. You know how, yeah, how many, how much paper you are trying to do. Well, do let us know. I mean, I can check my. If you were to hold these problems as well internally, I mean, I can't really do too much, but I think, yeah.
I was wondering in discussion, you know, the lines, so there's a lot of situation, so we want
Yeah, so when I have just going through the refinement. That is the best way. I mean,
Oh, really?
yeah.
Oh, that's so weird. Oh, so it's like, just, no one else.
It's nice. I think the sequences was. I'm actually solving some of them.
Yeah.
State of our model, they don't know that they're still or because of not the consolidation ways
No problem, but you said.
yeah, okay.
So
The work of
we can set it.
keep also the
That's fine.
yeah. And these are really promising because I do believe that the problem of one of the biggest problems is the definition. They get into this model of the definition of the complex field effective, learn to manage, the kind of really good preparation. But what I believe is that in order to have a different geometry without using annotations, retraining. So a way to measure is differential. For example, what I mean is that we found that you have a layout estimation, partial layout estimation. And another layout estimation. The only way that they define the lowest end is with
you help me set up my presentation?
the pole. The only
It's on PowerPoint.
yes, if both are agreement, so they will define the lowest edge. So the lower edge of it should be.
So you want to
Yes,
let's share?
a constraint in this. It's not being shared here when you don't have that. Because if you have already done. But if you don't have the next way.
Yeah. Sarah sent through 2 presentations for the Woodscape Challenge that need to be downloaded. I forwarded to your email.
Oh.
Can you download them?
All of the information.
I just need to go and check the poster. Sure. All right. I'm the one that takes those.
This is the one? Yeah, there's one folder which contains,
Yeah.
and one presentation.
To be honest, I have not considered.
whether we are disciplined.
What about the other one? Yeah, it should be this one. I just replaced the image, but it's easier to just swap. You can just go file download.
And yeah, it could be seen as a movie.
I guess there is a PPT already.
In for instance, you are just geometry. And one way, I guess it could be something related with the project that we presented last year for flow time estimation. But
Someone changed the name.
having
That's okay. Yeah.
Right. It's,
Oh.
quite realistic.
This one?
Never
Yeah.
get your corner.
It's and it's really
Good. Check.
give to the final user. More.
Right.
If we have an end-to-end model, so literally we focus on.
Or you can just open the link. You can make a shortcut, put it there.
And you estimate
Just fire the link.
have noise.
No, it's
And
easier.
then that moves you created the pseudo label that is needed for retraining the model or for train the model.
Right.
Yeah, I think there was something wrong with the conversion. Maybe.
Because the user just need to visit the camera.
That's PowerPoint. This
So,
is Google
For
site.
your multi-view.
Just create a
train
shortcut
that
from
type
share, I guess.
system.
Sure.
So
Yeah.
you have to
Let's
estimate.
say
Yeah,
create link.
yeah, in the.
Just copy
the
link,
paper,
maybe.
The route paper last year.
And put it in here. Yeah, right click new.
Entropy means secure for
Yeah.
coverage.
Yeah.
You know, the main problem with having the.
I don't know how to make a link.
is that the layout
There should
of
be a
the
way to
project
create a shortcut to
changes.
our web page, right?
So, if it works, you are estimating with a
No, it won't work.
now you have the scale of the digital dollars and the scale of the young.
Yes.
So we define.
Try to see if I can bring it.
that
I mean, if one wants to.
You go ahead. Yes, I guess we'll get started. We have two more speakers in the agenda, two exciting talks. The first one is going to be Shubhankar Bose. So he's a senior deep learning researcher at Qualcomm's AI Research Division, working on end-to-end perception with applications in autonomous driving, extended reality, and computer vision. He'll be speaking about the work on multimodal and multi-view bird's eye view perception for 3D object detection and map view segmentation.
Hello, everyone. My name is Shubhankar Bose. I'm a deep learning researcher at Qualcomm AI Research, and I'll be speaking on our work in bird's eye view as well as fisheye perception using multi-sensor inputs such as surround cameras and LiDAR. Thanks to everyone who's joining this talk, both online and in person, and it's a pleasure. So I'll now go over the motivation of using the bird's eye view perception approach. Most importantly, the BV space annotation is much cheaper than multi-cam annotation, and we can also reuse the same annotations as camera for other sensors like radar, ultrasonics, or LiDAR. Next, the bird's eye view space is translation invariant. It is invariant, like independent of the sensor type, and even independent of the distance and azimuth angle. So this in turn really simplifies tasks such as detection, segmentation, and re-identification. So the third thing is that with BV, we also allow the metrics to be measured in 3D apart from like 2D. And these are definitely issues in some KPIs when it comes to 2D measurement. So I think 3D metrics like would resolve that. And also like the BV representation kind of models longer range much better than the other perspective view approach. So as the bird's eye view can be expressed in 2D, it allows an efficient kind of feature representation compared to 3D. And it can, that's why, be faster on device. And I think that's our main purpose, to eventually put these models on device as Qualcomm. So finally, due to the fact that each modality and sensor can find a common representation in bird's eye view, it allows for a modular and end-to-end design. So you can just plug and play with different modules as you develop them. So here's the vanilla multimodal fusion framework that we used as a starting point, which was inspired from the BV fusion work done at Professor Song Han's group. And for any multimodal setting, we first process each modality with an independent feature encoder to transform it to a feature space. And the point cloud sensors such as LiDAR and radar will then initially be pre-processed by sparse encoders. The multi-view cameras pass through other feature extractors, which are off the shelf, and they're sort of mainly convolutional because we want to eventually put it on device. And then there's some sort of projection algorithm for both the modalities. So for point clouds, it could be something like a flattening projection. And for cameras, it's something like LSS, where you sort of transform the feature view from, the features from the perspective view to the bird's eye view. And then finally, we want to combine the features in multiple ways. And the vanilla method used is either concatenation or addition of these features. So once we combine these features, we can actually have separate decoders for separate tasks. So I think in this image, we are showing, 3D object detection and semantic segmentation done in two different decoders. So I'll probably go over them in detail as different parts of my talk. So in the first part of the talk, I think I'll sort of cover the BV map segmentation path from the previous slide. So we presented this method at WACV 2023 this year for semantic segmentation. It's called X-Align, and it is like an alignment method for multimodal map view segmentation. I have added the QR here if you want to access the paper. So this paper was accepted as a best paper award candidate at WACV, and that's why it's also been published at Springer. So we will start by talking about the motivation for our approach. Then I will sort of explain our contributions following which I'll give an overview of the proposed algorithm and then finally move to results. So the recent BV segmentation approaches such as HDMapNet rely only on cameras, which are constrained by the absence of reliable depth, of course. But some of the latest works, such as what we were inspired by, BEV Fusion, leverage both the camera and LiDAR modalities. But the problem with these approaches is that they sort of suboptimally fuse their features using a simple concatenation. So we wanted to take it forward. So maybe I'll move to the contributions of our work now. So basically, our proposed X-Align framework is a novel framework enabling better feature alignment across and fusion across modalities and views. So it consists of mainly 3 parts. The first one is this cross-modal feature fusion, or we called it XFF block, which is basically a strategy which sort of combines features efficiently apart from concatenation. The second part is this cross-modal feature alignment. So between 2 modalities like camera and radar or camera and LiDAR, we sort of want to have the features aligned in the same space. And this is sort of motivated by the fact that the LSS transform or any transform from the camera to from the perspective view to the bird's eye view is going to be kind of erroneous if you don't have the exact depth map, which we don't. So that's why sort of like, I think this XFA module or this XFA loss function sort of alleviates this this issue a little bit. And finally, we have like this cross view segmentation alignment. So again, this is between perspective view and bird's eye view. And it's basically an alignment function, like an optimization function to align like perspective and bird's eye view. So I'll sort of go to the proposed method in detail now. Look, so we start with like the bird's eye view fusion architecture as illustrated here and that I spoke about before. So to encourage the accurate view transform from the perspective view to the bird's eye view, we propose this cross view segmentation alignment or XSA loss. And this consists of an intermediate perspective view semantic segmentation. And then that segmentation is basically transformed to bird's eye view using the same shared parameters that transform the features. And then eventually we have like another supervision done at the end in bird's eye view space. Then the second module consists of like cross-modal feature alignment or XFA loss, which is basically a loss to enhance the correlation between the 2 input modalities. So right now in this image, it's like camera and LiDAR. So to enhance the correlation, because the camera prediction might and the LiDAR prediction might be sort of misaligned due to like maybe inaccurate depth. We sort of have like this loss function, which is trying to pixel correlate both of them. So right now what we used is the negative of the cosine similarity. So we are basically optimizing on negative cosine similarity between these 2 feature maps so that we push these maps to basically align pixel to pixel. And then finally, both these methods are loss-based and add no compute to the network during inference time. So they actually come at no inference cost. And for us, that's actually 0 cost because we don't really think about training when we want to transfer these approaches to on-device. So, but then we also wanted to study the effect of sort of adding more parameters to the network. And I think the place that we did that was the fusion between the camera and LiDAR. Instead of doing some simple concatenation, we sort of proposed 3 different approaches for fusing these 2 modalities. So for the XFF, like the cross-modal feature fusion, we proposed 3 methods for fusing the BEV features. The first one is like self-attention, where we concatenate both the feature maps, tokenize them using the patchification operation, and then apply like a self-attention operation. The second alternative that we proposed is like the spatial channel attention that is present in EdgeNext instead of the self-attention. So this adds a split attention both in spatial and channel dimensions. And finally, we also try like a pose-driven convolution scheme for fusion. So basically what we do is we input the pose matrix, the camera pose matrix into an MLP. And then we concatenate the output of this MLP to both the features, like the LiDAR and camera features. And essentially what we want to do with this concatenation is use it to drive a deformable convolution So technically what we are doing here is the kernels of the convolution or the offsets of this deformable convolution are kind of driven by the pose matrix, which is relative to camera and LiDAR. So if there is any difference in pose between camera and LiDAR, it's going to drive the kernels of the convolution, the deformable convolution. So each method here reduces potential misalignment between the input modalities, camera and LiDAR. But at the same time, like I mentioned earlier, it adds some sort of compute to the network. And we wanted to study what is the actual effect of adding this sort of compute. So what we did is we scaled up the baseline that we had, which is BEV Fusion. So we basically scaled it up in terms of the gigaflops. And we sort of went from we sampled 4 different points for gigaflops, and then we trained this model for 4 different instances. And then we tried to train this model with our 3 proposed algorithms for feature fusion, which was the pose-driven DCN, self-attention, and the spatial channel attention. So I think if you observe here, the best trade-off is available, I think, at the self-attention block. So we sort of kept that as our default XFF module, and then we move forward for the experiments. So yeah, now let's move to the results of our approach. So we sort of showed some quantitative results on new scenes. And in the 3rd column, you can see the modality. The modality is basically camera or camera plus LiDAR fusion. So we tried it for camera only approach, and we also did for camera plus LiDAR fusion. So as observed from the numbers, our approach X-Align performed better than the state-of-the-art methods in both camera and fusion modalities when we had submitted it last year. But for the camera only modality, we could only use the feature alignment loss or the XFA loss, as there are no 2 modalities to fuse. It is just a camera view variant. And that is why we call it the X-Align view from, I think, the 6th row in this table. So the X-Align view variant in the camera modality and the X-Align losses variant, which is the 2nd last row here, sort of improve the baseline by around 1.5 points in mean IU on average. But then one caveat is that they don't add any compute. So technically it's free of cost. But further, the X-Align all variant sort of improves over the previous state-of-the-art result by 3 mean IU points with a slight increase in model complexity. Okay, so here are some of the visual results on new scenes for, I think we have given 2 scenarios. So this is the first one. So we highlighted the improved regions in green, like you can see here. And so basically we show all the images, all the views of the car. So basically there are 6 cameras around the car, and then there's the LiDAR input. And then we have the ground truth, the baseline, and we show 2 of our variants here, X-Align view and X-Align all. So so basically, I think here the issue is that if you notice the road and the building, it's sort of similar colors. And when it so basically the baseline is not able to differentiate between the 2. So that's why you get this this error when you look at D column. So I think it sort of thinks that the building is the road and the projection is incorrect. But then I think our X-Align view and X-Align all variants were able to sort of alleviate this this issue. So then there's a similar improvement in the second scenario that we are showing here, where so in this one, the road markers are not clearly segmented if you look at the baseline approach. But then this is slightly better if we apply the losses. And then it's much better if we apply the additional compute, like you can see in this slide. So that one is with the fusion. Okay, so this is like a short and fast forwarded video of the final result on new scenes. So here we've projected all of the 6 cameras as well as the bird's eye view prediction on the right. And I think the car is just the reference point for each of the cameras. Okay, so we further show some ablation studies here, and this ablation study is very interesting because this kind of justifies the need for X-Align to make the network more robust to noise. So if you look at this graph, what we basically did is we added some input noise or some input Gaussian noise to the model at the camera stage. And then we sort of varied this noise by varying its standard deviation, which is present in the last 4 columns there. So basically like a high standard deviation of noise. If the X-line performs better than baseline, it would mean that it's more robust. And if you can see the graph there, the baseline sort of, which is the BEV fusion approach, sort of drops quite steeply as compared to our proposed X-line algorithm. Okay, so this was the summary of the first part, which is the BEV map segmentation of my talk. And basically we proposed X-Align, which is a novel framework, which sort of enabled better fusion as well as alignment across 2 modalities for map segmentation. Okay, so now let's move to the second part of our talk, which is the 3D object detection model. So for this algorithm, so basically I'll be presenting this algorithm tomorrow in the main conference. We called it X3KD, which is abbreviated for cross-task, cross-modality, and cross-stage knowledge distillation for 3D object detection. And again, if you want to find the paper, you can sort of scan the QR code here. So I'll start by sort of talking about the motivation for this approach, and then explain our contributions, following which I'll give an overview of the results and then like a small summary, similar to the previous paper. So in this one, it's a very simple motivation. The motivation is to sort of reproduce the performance of the LiDAR-based 3D object detection to other modalities such as camera and radar. Along with this, we also wanted to utilize the labels from the instance segmentation task to develop richer and semantically aware features for 3D object detection. So this motivation feeds directly into the major contribution of our work, which is to improve the current camera-based backbone by distilling from a LiDAR teacher network to perform some cross-modal distillation. And we also perform cross-task distillation by distilling from instance segmentation to 3D object detection. Okay. So let's discuss the proposed method in detail. So we start with a BEV depth baseline model, which computes the depth and uses it to transform to perspective view. So basically it uses it to transform to perspective view in terms of the camera features to the bird's eye view space. And this model supervises its depth prediction by using the projected LiDAR points during training. So I think here's like just a snapshot of their results, and then we compare it with our results in this slide, with MAP and NDS being the 3DOD objectives. So as we discussed earlier, LiDAR models perform much better than multi-camera or radar models on 3DOD, but the components of all these models, like I'm showing here, they're kind of structurally very similar. So if you notice, there is a feature extractor, there's a BV projection, then there's a BV encoder, and then there's also like a final prediction head. So another point to note is that during the transformation from perspective to the bird's eye view, camera-based detectors focus very strongly on the center grid cells, and the effect is much lesser around overall. So that's what you can see in this image in the bottom right, where the effect of the LiDAR-based BV feature activations is much more spread out as compared to the camera-based, which is sort of like, it's sort of like aggregated towards the center. So hence, like one of the major points of our focus for our distillation is the feature map right after the transformation block, like right after the BV transformation block that we highlighted here. So let's look at the camera student again and the LiDAR teacher once again. So the first stage of distillation, as motivated from earlier, is the cross-modal feature distillation, or we abbreviated it as XFD, which learns to predict the uniform LiDAR features from the camera. And for the next stage of feature distillation, we focus on the BV features right after the BV encoder and decoder. So here actually we apply like an adversarial loss between BV features of LiDAR and BV features of camera. And then I think the objective of the adversarial loss is to make sure that the network is not able to differentiate between, or we are not able to differentiate between whether they are BV features from LiDAR or from camera. So it kind of stops this the aggregation in the center and tries to spread out the feature map. And then finally, the last stage of the multimodal distillation is at the output stage, or XOD, which directly compares the bounding boxes generated by the LiDAR teacher and the camera student. So we also pre-trained the image feature extractor on the student to perform a different task. So instance segmentation that we had observed earlier sort of made the network or the feature extractor better if we had pre-trained it on the instance segmentation task and then transferred this to 3DOD. So motivated by that fact, what we did was to retain the semantic understanding during training. We proposed to sort of distill basically we wanted to apply like a cross-task distillation between 3DOD and instance segmentation, but during training time itself, so that it sort of retains this ability of semantic understanding. So this concludes our explanation for the approach, and let's move to the results again. So in this slide, you can observe the improvements obtained by LiDAR distillation on a camera student. We compared our X3KD algorithm with other recent approaches on like the same backbone. So we would keep the same backbone like ResNet 50 or ResNet 101. And you can see like a significant improvement over all the previous approaches. But I think the main point to note is the improvement over BV depth, which was our baseline model. So the BV depth model and the X3KD model have the same exact architecture, and it's just a different training scheme. One thing to note, so basically apart from like a smaller resolution, we also tried like the larger resolution, which is 900 x 1600 in camera, and we observed like similar results there too. But one thing to note is that again, X3KD does not add any additional compute during inference time. So again, these improvements are technically at no cost to us. So similarly in this slide, I think I'm showing the effect of distilling LiDAR to a radar or a camera plus radar student. And the cam radar fusion model here was actually top of the new scenes public leaderboard. I think the last row in this table was top of the new scenes public leaderboard when we submitted it. But I think this is very interesting because it shows how the LiDAR, which is much more expensive, can distill into radar, which is a much more cheaper sensor, but still probably has that range that camera doesn't. Okay, so here are some of the visual results comparing a solution to BEV depth, which was the baseline student model. So distillation from LiDAR helps to improve the projection from perspective view to BEV. And if you observe the white boxes that are present in BEV depth versus X3KD versus the ground truth, you'll see that the alignment of the cars is much better in X3KD as compared to BEV depth. And this is probably because of the projection. And if you notice the same cars in the camera view, they are sort of tilted, but then they sort of get straightened out in the bird's eye view. And that's much better shown in X3KD model compared to the ground truth BEV depth. So again, here's a short and fast forwarded video of the final result on new scenes. So here again, we projected all the 6 views of the camera. And I think the front is right in the middle, like the center top is the front view. And right below that is the back view. And then there's like prediction on the LiDAR, prediction projected on the LiDAR. And then we also have prediction projected on the bird's eye view space. Okay, so in summary, we presented our training method comprising of distillation from LiDAR to camera and to radar students. And the distillation was performed across tasks, across modalities, and across stages. So it provided significant improvements at no cost during inference time. And again, I've added a QR code here, so you can check it out. We'll be presenting the poster tomorrow morning at the main conference. So, okay, so let's move to the third and final part of our talk, which is the multi-camera fisheye perception model. So let's go over the setup for this, as this method is on an internal collect and not a publicly available data set. So in this one, we have 4 fisheye cameras around the car and a pinhole camera at the front. And the fisheye cameras have a field of view of 186 degrees, which is much better than the pinhole camera, which has like just 120 degrees field of view. But the pinhole camera has a higher range, as you know, compared to the fisheye cameras. So sort of to account for the radial distortion caused by the fisheye camera, we performed warping. And I think this is done by first warping the fisheye camera to a spherical coordinate system using a lookup table. And basically we went from the fisheye to world coordinates in the spherical system first. And then once we did that, we projected it to 2D using 4 different representations like cylindrical, Mercator, stereographic, and equirectangular. And I think empirically we observed that the equirectangular projection had much better performance, or the best performance. So we stuck with that. So once we perform the warping, we use like a decentralized approach to perform 3D OD. And each warped view goes through like a CNN detector, and then finally like a patch refinement CNN, which reduces some of the false positives. And once we do that, then there's like a tracking approach done at the very end to sort of track and re-identify boxes along frames. So this is the result. It's not playing. Oh, that's too bad. I think the result is not playing, so maybe I'll just leave it. Okay, so basically, in summary, we presented 3 of our works. One of them was bird's eye view segmentation, one of them was bird's eye view detection, and then finally, like the fisheye surround camera algorithm. So yeah, I think that's all for my talk, and thank you. Just let me know if you have any questions. Okay. Thanks.
I have a question. First, I'd like to know for you, what is the critical part still no able to accomplish the burden
Okay, so I think the main thing is right now the algorithm we did for semantic segmentation and bird's eye view, that is just a part of the ground truth annotation pipeline. So as Qualcomm, we would want to move it to device as soon as possible because we want to move it to our chip. But right now, I think the algorithm is still in the stage of ground truth annotation. And then I think the main part there is the sparse. So basically, like the LiDAR and the radar point clouds have to go through like the sparse encoder, right? So mapping the sparse encoder to device has like a lot of problems. So once that is sort of solved, we can actually put it on device and run it real time on a chip.
Great, great. And my second question is in the last work that you presented, you mentioned that you use different fisheye cameras and then you project it into a rectangular.
Yeah.
And you mentioned that the rectangular projection would be better than the other projection.
Yeah.
Do you have any clue about why that happened in that particular camera projection?
Right.
The symmetrical one has more. We can say that it has only one degree of distortion. Just
Yeah.
cylinder.
Yeah.
And why the rectangular event has that particular case?
Yeah, I think that's a great question. So what I know is empirically we found that the equirectangular was better than cylindrical, and maybe it's because of the distortion that was on the sides. But yeah, again, like I'm not sure what exactly the reason was, but empirically we just probably found that that had the best result. So, yeah.
Do you think that maybe it's related about the orientation of the cylinder?
Yeah.
Because I believe that the main problem with the rectangular image is the distortion
On the tops, yeah, on the
but
poles,
we are focusing only on the in the center of the image, so that
equator, right?
We will have a better performance distortion.
Yeah.
But for the spread. For the cylindrical one, basically we don't have the pole.
Right. Yeah. So I think the issues with equirectangular, like you said, are at the poles, and usually like I don't know what a level of performance is attributed to the poles, but because those are like the sky, I think like that sort of maps to the sky mainly, and maybe the distortion is there. So when there's like a clear road in front of you, it's probably along the equator. So maybe that's why we observe like a better representation with the rectangle.
Okay, thank you. Thanks for the great work. Thanks for sharing. Wondering what your thoughts are on synthetic data and what role that might play here. I think everything you did was with real data, right? Right. And using LiDAR.
Yeah. Yeah. So I think synthetic data is pretty good. I think what we could do is have like a system which is combined between real data and synthetic data, and that could sort of generate much better annotations. And I think that's what we are doing right now. So the current system that we have is with real, but then there's like a hybrid approach where we are using both synthetic and real to eventually get that performance.
So it's coming, right?
Yeah, definitely. Yeah.
Thanks, that was a great talk. So next up, we have Professor Adrian Hilton. He's a professor of computer vision, founding director of Surrey Institute for People-Centered AI, and director of the Center for Vision, Speech, and Signal Processing at the University of Surrey. The focus of his research is perceptual AI, enabling missions to understand and interact with the world through seeing and hearing. This combines the fields of computer vision and machine learning to develop new methods for reconstruction, modeling, and understanding natural scenes from video and audio. Since joining CVSSP in 1992, he has led research in 3D and 4D computer vision exploited in entertainment, manufacture, and care industries. He has received 2 EU IST prizes, a DTI Manufacturing Industry Achievement Award, and a Computer Graphics World Innovation Award, 8 Best Paper Awards in international journals and conferences, and co-founded the European Conference on Visual Media Protection. Today, he's going to talk about audio-visual 360 scene analysis for acoustic modeling and augmentation. So let's welcome Professor Hilton.
Thanks very much, and thank you for the invite to present at the workshop today. So I want to talk about a bit of a different problem, which is essentially how do we embed audio into an augmented scene? You might think, well, why am I talking about that at a vision conference? Well, you know, we do lots of work on visual reconstruction. We've seen lots here today and across the conference. But one of the uses for that is actually to augment environments. And the part of that augmentation should be to augment the audio environment as well that we're in. And if you think about content and entertainment experiences, they're as much about the audio that we experience as they are about the visual elements. We don't like to say that because we're all computer vision people, but we need a balance there. So what I'm going to talk about is some work actually led by Hanson King, my colleague, that's essentially looking at using vision to support audio augmentation, and in particular using 360 cameras to do that, which is hopefully how it fits here. So we want to generate immersive experience. We want to augment the real world, real scenes with audio. And in order to do that, we have to embed the spatial characteristic of the space, the room that we're in. Otherwise, it won't be plausible. Yeah? So when I speak in this room, the audio is, of course, bouncing off the walls, and it gives us a presence in the room. If I just put you into an augmented reality environment and played back my voice, it's going to sound very odd. It's not going to sound embedded in the environment. So that's the key. So what we need to do is be able to model the space and actually have knowledge of the acoustic characteristics of that space. What I want to talk about is some work that we've done to look at how we can use vision to support that. So the obvious starting point is to build a 3D model of the scene, but that's not enough in itself. So we have to add some layers on top of that to extract things like the material properties of the scene from visual information, and actually to close the model so that we can put it into an acoustic simulation as well. So this is a whole bunch of work in that space. So the key to this is really, you know, what does human perception rely on? Well, it relies on both the audio cues of the environment, actually very, very important to have presence in an environment, to have the right audio cues, as well as the visual information. And those two things need to be coherent. They need to be, they need to match, essentially. So what what we want to do is then take the audio side of things and embed it with what we see in the environment. And that's been shown to be very important for presence in virtual and augmented environments. In this case, the most interesting case is augmentation rather than just creating a purely synthetic model, where we can effectively do that using graphics engines and things like that to embed the audio, to render the audio as well. So, as I said, we've got lots of work on visual modeling. We see lots of work here. And I would say this is one of the uses for this. It's quite an advanced field. And we know how to render sound if we know about the environment. But what we don't have is a set of tools for actually taking an image or taking, in a simple way, some capture of a room and producing an acoustic model of that environment. Okay, so that's what we're looking at here. How can we do that? And that acoustic model needs to embed both the shape characteristics and the surface acoustic properties. So if you transfer into the audio domain, then how is this done? Yeah, of course we can do it. We can measure room characteristics. We can measure the room impulse response. And essentially that's done by placing a microphone in the room at a particular location, placing a sound source in the room, usually an impulse, and measuring the response. Okay, how far does that actually get us? That gets us to the point of knowing what the characteristics are for that particular sound source and that particular microphone location. To do that and map out a complete environment in terms of the audio characteristics is a very tedious process. You know, it's not something you're going to want to do in your living room, let alone, you know, capturing the spaces that you maybe want to augment. So the question we're addressing here is, can we use visual information to acquire some sort of acoustic model of the scene? And that model is going to comprise information on the geometry of the scene, the shape, which is important, and also an estimate of the acoustic characteristics. Now, I just want to stress, that's always going to be an estimate because we're using visual information. And if you think about it, I've got carpet on the floor here. That's nicely absorbent acoustically. But visually, that actually could be a concrete surface that just happens to have the same color characteristics and would have a completely different acoustic characteristic. It would be much more reflective acoustically. So there is a limitation, there's a fundamental limitation as to what we can do there, but it's interesting to see how far we can get. And most of the time, if you make those assumptions of, well, I can detect which materials in here are soft furnishings, which ones are carpets, which ones are likely to be walls that are made of plaster or something like that, that will reflect the sound, that gives me an approximation of the acoustic environment. So that's essentially what we're going to do here. Okay, so we want to move. Oh, okay, good. So there's another important feature here, which is we're not trying to achieve physical accuracy. And that's really important. Why is that important? Because physical accuracy would require a lot of measurements. There's no way around that. But what we need to do is actually create something that's plausible, that fools a person, that the audio is correct for that environment. And that's a much weaker constraint, if you like, on what we have to do. And you know, in the case of a virtual environment, that means that your internal reference there is what you see in terms of the rendered scene, and your audio needs to be coherent with that. In terms of augmentation, you have an external reference, which is the room environment that you're augmenting. And so you've got that external reference, and your spatial audio needs to be consistent with that scene that you're seeing. Yeah. And your brain will tell you if there's some incoherence there. Essentially, we're very good at that because we're very used to mapping the characteristics. Okay, so hopefully that gives a bit of a motivation behind what I'm going to talk about. essentially I'm going to talk about a pipeline of algorithms that have been put together as a, if you like, a first pass of doing this to get us to the point where we can have a simple capture of an environment and then render audio into that environment. And lots of the modules I'm going to talk about could be replaced with other methods that you've seen at this conference today, or you'll see over the course of this week. But it's a proof of concept, essentially. And the assumption is that we can get close enough to an acoustic model that you won't recognize the difference. And we evaluate that in the end in terms of the audio rendering. So there's a whole chain of different processes here, which I will go through to illustrate what we're doing. So this is kind of the overview of the methodology. And we're starting from 360 imagery because that's actually a very simple single shot way of capturing, at least from a single viewpoint, capturing what you can see in an environment. Of course, there's a couple of limitations to that. One is that at any given location, your 360 camera won't see the whole scene. It will be occluded in this environment behind all the chairs, for instance, from where I'm standing. But it gives us some information about the geometry of the scene. We can then build semantic information on top of that, and that takes us towards a model of the environment. And then in addition to that, we can use appearance information to estimate materials in the scene. So that's essentially the process here. And then in terms of then embedding, augmenting that scene, well, you have to reproduce the sound at the listener, the viewer's ears. So you need to be able to also track the person. I'm not going to talk about the tracking work today, also lots of tracking work in the conference, but essentially we'll get to the stage where you can then have a model that you can use to augment the audio within an environment and the visual characteristics if you want to. Okay, just in terms of explaining where we need to get to with the model, then there's a lot of work on acoustic simulation, but it assumes that you have a model of the environment and every surface in that model, you know the acoustic characteristics, so essentially how it reflects the sound. Once we've got that, then we can model the reverberation within that environment. So we can reverse engineer the room impulse response with respect to any location that we want, any location of sound source and any location of listener within that environment. And that's what we need in order to reproduce the audio. Something that's really important in this is that that model is complete, it's closed. Because, for instance, at the moment, the door at the back of the room is open. That will make quite a big difference to the sound characteristics of the space. You think if you've got windows in a room, whether they've got glass in them or not, makes a big difference to the sound characteristics. So you have to have a closed model, and you want to have all the surfaces that are major reflectors in that scene. The good news is that you don't really need the detail. You need a relatively crude geometric model, because the main thing you're interested in is the main sound reflectors in the environment. So the fact that there's a lot of clutter on the podium here makes very little difference to actually how I'm hearing the sound in the room. Yeah, so it's about getting a coarse model of the scene that's complete. Okay, so let's go through the different algorithms, and I will whistle through this. It's already taken a little bit of time. So the first step is to use essentially spherical stereo to get a depth estimate. That's one way of doing it, and it's actually a very simple way of doing it. So we just take a vertical pair, in this case of Ricoh theta cameras. That gives us a very simple geometry, essentially a one-dimensional search for the stereo correspondence between the cameras. And as long as you know the baseline between those cameras, you can reconstruct 3D. It's not going to be hugely accurate, because if you're measuring, for instance, across a room like this and you've got a small baseline, that's the error is going to be quite large, but it will be good enough for the application that we're looking at. So this is one way of doing that, and it's the way we started out with. So you use your spherical geometry, you triangulate based on correspondence, and you can work out distance essentially from the camera, and that gives you a 3D model of the scene. This work was done, well, actually it overlaps with deep learning, I suppose, but it was pre-deep learning really. So it's a classical stereo method we used here, a variational stereo that gives us a smooth surface. And it's an energy minimization. If anyone remembers that, that's what we used to do in Vision before deep learning. Of course, this could be a deep learning method as well. The question would be where you get the training data from. You know, in this case, that's quite tricky. And essentially, what this is showing is just the depth map estimated at the bottom. And if you just do a raw stereo correspondence, that's the case in the middle, but it gives you a reasonable geometry of a room environment. We've also looked at single view depth. Again, the key challenge here is the training data. There's not vast numbers of 360 images. So you need to do some sort of modeling, domain adaptation to train your method. I won't go into the details here, but there's references in the presentation, and you can get reasonable depth maps with that kind of thing, reasonable estimates up to scale of an environment. And we have some refinements to get around the fact that you have this domain gap, and you need to essentially adapt to real world data to get depth information out. So we've done a bunch of work in that area to essentially allow us to do single view 360 depth estimation, and it works well enough, I would say, for the purposes of what we're trying to do here. And that's of course being evaluated. The algorithms work reasonably well. Okay, the second step is material estimation, and here really what we want to do is estimate acoustic characteristics, but we're doing it based on appearance. Now it's a slightly dubious assumption, but that is what we're going to use here. And essentially the appearance in here, I mean, I would say the chairs have soft backs just from the appearance. That's the kind of assumption we're using. Doesn't mean to say they do have, although I've sat on one and they do. So this is a material labeling, segmentation of the scene, and the things we want to use are both global and local features of the scene. And I'll show in the next step how we build in semantics information as well. But essentially, learning-based approaches where we're propagating information using local patches at multiple scales to classify materials. And there's some refinement of that with a transformer network to focus attention across multiple scales and get around some of the problems we have with the 360 imagery of the scene. Okay, so that gives us, and you can see here that some sort of segmentation. DBAT is the method used here, but it's quite crude. Doesn't really do a great job, and that's because it's not actually segmenting out any object level information. So what we've gone on to do from there is look at how we can put semantic information into the scene and build these kind of block worlds from this. So we have a line of research that's looking at 360 imagery and essentially learning how to construct models, but how to construct complete scene models rather than just partial models. And that's essentially learning from, we split up the 360 scene into a series of depth maps of the scene. The reason for doing that is there's lots of training data for depth maps, which we don't have for 360 imagery. And that starts to take us in the direction of being able to build up complete models and label objects within the scene. So that's essentially what we're doing with these architectures. And one key thing that we found makes a huge difference actually here is not just to do a semantic labeling, but to leverage the edge information in the images as well, because that really refines the boundaries of the objects. So that's built into the network with this EdgeNet architecture, or EdgeNet 360 architecture that we built. And that allows us to go from the 360 images through to a complete representation of the scene. Okay, so at that point, we're then able to start the audio rendering given acoustic properties. I'm not going to talk about the human tracking today, but essentially that then allows us to put together the room impulse responses that we need to augment the environment. And if I just run through this, is essentially information on how you do room impulse response. But essentially what we're then doing is taking that model and putting it into a headset, either as a virtual environment or as a real environment. I'll just whistle through to the videos at the end here for a variety of scenes. You can see these are rendered views with audio, but there's little point in me playing back the audio in here because you need to have a headset on to hear the differences. But it really does make a difference to well, you will hear the audio. You should be able to hear a difference when the geometry in the scene is switched off. So this is one particular scene that's been modeled. Very little difference in the playback in here. But you can actually, without essentially the difference you'll hear there is without any objects in the scene, there's nothing to absorb the sound. Yeah, so you get very reflective. As you put objects into the scene, it breaks the sound up, essentially. You can probably hear it at about that level. So I'll just play through one more video. So this is now augmenting actually music in this case into a virtual environment. You can see on the screen behind. Sure you can hear any difference there. Okay, let's just play it. Okay. So this is a real environment that we're now augmenting into, but we have a full 360 model of the environment. And essentially it's rendering the audio for the particular location. The big sphere that's floating there is the sound source location. So it's just a representation of that. So the audio doesn't come through too well on that. So just to wrap up, really, so what I'm proposing here is a vision-based approach to capturing the acoustic characteristics of an environment. And what we found, and there's a whole load of subjective testing behind this for the augmentation or rendering in virtual environments, is that you get a reasonable model. So you need simple geometry, you need the model to be complete, and the bit that's a bit dubious, I would say, is you also need to estimate the acoustic characteristics. And we're doing that in this case from the visual information. What I would say is it definitely does a much better job than if you don't model the environment, but there's some pretty broad assumptions there in terms of acoustic characteristics. So that's probably an area where you could do more work in this direction. And I would just go back to the beginning really and say, why is this important? Well, as we move into a world where that boundary of augmentation of our environment changes, then actually augmenting the audio environment in that space is going to be really important. Yeah, if you think about, okay, you augment an environment with a bunch of people sitting around a table to have a meeting. That might be something we want to do in a work environment. You know, it's really important for presence that the acoustics of those people match the environment that they're sat in. Otherwise it will break. And that's one of the reasons that virtual and augmented meeting spaces don't work particularly well at the moment, is that that's often left out. So I think vision has a role to play here in getting us to a place where these things become very practical to do. And with that, I'll wrap up and say thank you.
You have any questions? So I do have one. So you mentioned about the single 360 depth estimation. I was wondering if it's up to scale or.
It's up to scale. Yeah, it is. So,
how do you do that?
So, yeah, sorry. So you've got a scale ambiguity in there. Yeah.
Yeah.
So in order to remove the scale ambiguity, you have to put some size information in. We would use for internal environments, we'd use door frame size. You know, the height of the door is fairly standardized. So things like that you can use. Is it accurate? It's not 100% accurate.
Okay.
Yeah, not like taking a LiDAR, but it's good enough for this application.
Yeah. Thank
Thanks very
you.
much.
Thank you very much. That was a great chat. So to finish the workshop, we have two more challenges to present. First up, the Woodscape Challenge. Saurav Balaji from Value will present the Woodscape Challenge Award. He's a deep learning and computer vision AI researcher working in the R&D team at Value Vision Systems. He has previously completed his PhD work at Maynooth University. He will be presenting the Woodscape Challenge today. Oh, yeah, sorry. Yeah. Yeah.
Hello, I'm Saurav Balaji. People call me Saurav, first 5 letters. So, right. So I'd first like to introduce you to the challenge organizers. This may be the longest name here. And it's John from Maynooth University. So I was in Maynooth and I started this, and now I'm working at Vallejo. And Omar, Nate, and Philip are from part of the moon, and Jonathan and Ganesh are from Vallejo as well. And Jonathan has now moved to Jaguar. So we had the challenge running for the past 2 years as well. 2021, we had semantic segmentation challenge, and in 2022, we had object detection, 2D bounding boxes. And if you're wondering, for this year, it'll be easier. No, it's motion segmentation, a harder task actually. So what exactly is motion segmentation? So we're going to have 2 input images, the current frame and the previous frame, t and t-1, and we need to find which objects are moving. So so this is one image, and let's say those are the 2 images. You can see a lot of things look like they're moving, but the actual ego car itself was also moving. So these are the only 2 objects that are actually moving. So the others are actually not moving, because it looks like they're moving because the ego car is moving. So this makes this an interesting task and a hard task as well. So why fisheye? Of course, because we get more perceptive field, and we get more information from the cameras, and they're very well suited for many applications, including self-parking and a lot of things. The narrow field cameras are suited for example, high-speed driving, but for many other tasks, we would need more image content to process. So this year, of course, we wanted benchmark techniques for motion segmentation on fisheye images. So we hosted it on CodaLab from April 5 to June 4, approximately 2 months. So every year we used to give the Woodscape dataset, and participants would download it, use that to train. And this year we did something interesting, and we also have synthetic data. We release synthetic data so this is from Parallel Domain, who's also sponsoring this challenge. So the real world data is from Woodscape, of course, and the goal is to maximize the results, the KPIs, key performance indicators, using synthetic data. Why do we do this? Because of course we can't keep collecting more data, keep annotating data. It's going to be more expensive, and we can use synthetic data. We can do a lot more with it. So on that thing, Omar is here. I'd like him to talk a little bit about synthetic data. So he's from parallel domain. I'd hand the dice over to him.
Thank you, Sir. Not going to take much time, but thank you so much for inviting me. Hi, everyone. My name is Omar. I'm from Parallel Domain, Director of Product Marketing. Yeah, we're really excited to collaborate with our friends from Valeo on this actually competition because for a couple of reasons. First, for the task itself, we thought like this is a really good use case for synthetic data because like labeling motion is really hard, right? Like it's easy to relatively easier to rub on the boxes, maybe do some seg and stuff, but to understand or teach the human annotator which object is moving versus not, especially with the example that Sarab showed, that was pretty hard. So the motivation was like, hey, can we solve that problem using synthetic data mostly and less real data, which is exactly what happened in the competition. I don't want to do a spoiler, but you're going to see that the results that the contenders achieved actually were with less than 25% real data and just synthetic data from parallel domains. So just want to say that I'm really excited. We were able to provide 4,200 scenes with different types of annotation, 2D, 3D bounding boxes, semantic segmentation, instance segmentation, and motion masks. And I was really impressed with the results that the contenders achieved, and definitely excited about what synthetic data can bring and collaborating with our friends on more and more challenges. Thank you so much, sir.
Right, so back to the competition details here. So, and we also introduced a penalty because we are going to ask the contestants to use only 1/4 of the data, 25%, and they need to use this wisely they can do joint training, they can do fine tuning, but if they use more data, then they're going to get penalized. So the IOU, the intersectional union will be taken, but there'll be a small penalty applied if they use more than 1/4 of the data. This is to encourage using more synthetic data and to do more techniques like domain adaptation and fine tuning and such techniques. So, and the two data sets, of course, we have Woodscape and parallel domain. We have about 10,000 images from Woodscape, so of which 1.7K are test samples. So we had two phases, the train phase and the dev phase, the train phase and the test phase. During the train phase, a subset of 500 images were evaluated, where they were all evaluated in the test phase. So with parallel domain, we had more images, 16,960 training and validation images, to be exact, and those are spread across the 105 different scenes. And we also released more labels as well for the participants to use if they needed it. So, and this time we did not allow any pre-trained models, which means they have to use the synthetic data in order to improve the accuracy. So as I told, the competition was held in two phases. Once again, this is to avoid any data leaks, or the information leak that they might actually figure out from the leaderboard. For example, participants might keep looking at the scoreboard and then change their model, and that might not actually reflect the true performance. So we need to keep aside a small subset for the final test phase. So we had a total of 112 global teams, and we had 234 submissions in total. And finally, for the leaderboard, so that's the leaderboard with the top 10 displayed over here. And to give us a rough estimate, we had trained a ResNet 18 based baseline, and the score was well below 0.1. And you can see that the submissions here have a lot more score. So we trained the baseline just throwing the data that we had from without doing any fix. So that to give us a good estimate of what it would be if they used a ResNet-based backend and then just trained the data. And the winner is Star with the username www. The team members are Foxing Leng and Shenlong Yi from ByteDance and HUSD. So they'll get a reward of $2,500 and I'll let the winner present their results. To switch. Yeah, he's already there. Oh, we're Foxing Leng.
So, wait, publish here.
Yeah, it's fine.
Are they sharing?
So just have to allow sharing. So Foxing, can you start sharing your screen?
Fuxing, can you hear us? Can you share your screen, please?
Sorry, I'll open the PPT query.
Okay, we can see the screen. You can go ahead.
Hello, everyone. We are the starting. I'll show our solution for the OMI CV 2023. This is our team composition. I'm from ByteDance and my partner Cheng Rongyi from Huazhong University of Science and Technology. Let's review the task of this challenge first. This challenge is a domain adaptation semantic segmentation task for moving object, which provides synthetic dataset, parallel domain, and real-world dataset woodscape. The dataset provides previous image, RGB image, and moving segmentation label. It should be noted that woodscape only less than 25% can be used to fine-tune model. The evolution score is 0.02 static MLU plus 0.98 motion MLU. Then introduce our solution. The first is data split. In the first stage, we use a mixture of full synthetic data and randomly sampled 2,000 real data to pre-train the segmentation model. In the second stage, 2,000 real data are used to fine-tuning the model. So the first stage model is pre-trained initial the second stage. We experimented with 3 input methods. The first is to directly input the RGB image. The second is use the RGB image to subtract the previous image. And the third is to use the RGB and the previous image to calculate the optical flow and add it on the RGB image. So we experimented the 3 input methods. In terms of
Pushing, your voice is breaking, so we cannot hear you. Can you hear us? We cannot hear you from the main conference.
Foxing, can you hear us? We actually can't hear you. Wait, or do we just wait for him to finish? We can only see the slide stuff. Sorry for the technical difficulty here. Many congratulations to the winner. Unfortunately, we couldn't let him continue because of the technical difficulty. So I'll move on to announcing the second place and the third place as well. So the runner-up is USDC, IIT United. So they're from University of Science and Technology of China. So they'll be rewarded with $1,500 and unfortunately they're not able to come here or present online. So but they have a recorded video which I'll be playing now.
Yeah. Stop sharing the Zoom.
Yeah, need to share it.
Hello everyone. I am learning you. Please see how solution for Woodscape fish and ocean segmentation challenge. Our affiliation with University of Science and Technology of China. Firstly, I'm going to talk about the dataset and what makes it challenging. This challenge consists of two data. Woodscape dataset and parallel domain synthetic data. Woodscape comprises sports around view fish and cameras in 9 tasks, including segmentation, depth estimation, 3D bounding box detection, and the novel soiling detection. To make an integration of more than 40 classes at the instance level is provided for over 10,000 images. The parallel domain data, consisting of 105 to 0.7 daytime scenes, is twice the size of the Woodscape data. The 4 fisheye cameras are simulated on the rendable cloud cover across 4,200 viewpoints, which are annotated with 2D and 3D bounding boxes, semantic segmentation, and instant segmentation. This is a brief version of our segmentation method. We conduct supervised learning on the labeled data through the above 4 models. And finally, we fuse the 4 models through the voting method to obtain the final solution result. Now, I will describe our proposed method in detail. We train the model using only parallel domain images, only 25% Woodscape images, and some training runs using a combination of parallel domain images, and 25% Woodscape images, random partition, we evaluated all as key. Living methods are our predefined validation set to get the best partitioning of the data. The fact that having synthetic parallel domain data is striking. This is the training time of our 4 model methods. The hardware environment is for NVIDIA Tesla V100 GPUs. This is our related training and inference strategy in which different data augmentation methods are used for different models. This is the structure diagram of the image Ethernet model. In the training process of using this model, we use the data augmentation method of random crop, random click, photometric distortion, and pattern. We use random click method built inverse augmentation. This is a mapped 2-corner swing model structure diagram. We use the data augmentation method of random size, random crop, random click, and photometric distortion during training. We use photometric distortion method during inverse augmentation. This picture shows the structure of the Ethernet and the convex sound model. In the process of training, we use random person size, random crop, random click, random mosaic, photometric distortion, having data augmentation methods. We use photometric distortion method during inverse augmentation. This is the segmented model structure diagram. We use the data augmentation method of random size, random crop, random clip, photometric distortion and padding during cleaning process. We use random clip method during inverse augmentation. This is a set of comparisons. It can be seen that the mask is more accurate after the voting of the 4 models. This is the performance of different data on our local validation. The model is three-plate, three-pass. In this section, you can see the huge impact of including synthetic parallel domain data to our training. Our baseline for local validation does not use any data on it, and the MIOD metric is 25.57. After that, we did a series of evaluation experiments. The table lists all the effective data objects. This table shows the performance of different voting methods on that phase. You can see that a fusion of the 4 models through the voting method has the best effect. Finally, we got 0 points for 7 score at our final result, which placed us second in the challenge. Finally, you can see that our method is very effective for workscape push-and voting segmentation. Thanks for your listening.
So you want to share the link? Which slide?
It's actually not there, it's that PPT.
All right, so where?
It's okay, I'm out.
Oh. This is the third one.
Yeah, it's the third one.
Let me see if I have this here. No. Okay. This is the one.
Yeah.
I haven't shared the screen.
Yeah. Congratulations for the runner-up team. And the third place team is XMU UAV with a username Hebayon, and they'll be rewarded with $1,000 US. Unfortunately, they are not able to be here either, and they can't present for some unforeseen circumstances. So we'll be concluding this one. So we were very excited to conduct this challenge and to see the results and to see the efforts that they made and the different methodologies that they used in order to improve things. And after including the synthetic data, many reported that the toppers reported that they had got significantly higher results. And going forward, it'd be a trendsetter that given in many places where we can't actually label the data, synthetic data will be used in order to improve the key performance indicators in many tasks. Great, thanks very much. And if you have any questions, please let me know.
Yep, thanks, Sarah, for that. So to close up, we have one more challenge. I'll be presenting the challenge. It's a quite interesting one. So yep. Let me share it. First of all, thanks everyone for joining our workshop today and sticking till the end of the workshop. So today we just dig into the odometry challenge, and so we also this challenge with one of our own non-automotive data set that we published in cooperation with Technical University of Ilmenau from Germany. So let's just dive right in. Okay, so this is our first year hosting a challenge in this workshop. Just a quick word about our company. So we are a specialized software AI company based in Germany. We primarily develop and distribute safe AI algorithms for semi and fully autonomous vehicles like drones, cars, trucks, and air taxis. So our core technology involves fusioning different sensor modalities like camera, radar, and LiDAR. And that brings us here to the odometry challenge. So what is the task? The task is to develop an odometry algorithm that can track motion of a drone through a forest environment using fisheye camera image and LiDAR point cloud. That's the data set we recorded during different seasons of the year with different trajectories. So you can see in the screen, summer, winter, and spring images of fisheye, and then the LiDAR data set of the same. So why do we even need a forest data set? Forest data set help foresters to encourage the ecosystem research, and such a data set gives researchers a better understanding of the forest stand structure and dynamics of the forest, which in turn helps to interpret human activities in the ecological system. So they have been doing it for years. They have been doing it manually, with which is time and manpower intensive. So you have to go and like measure each and every tree in the forest area. So which is, as you can imagine, is a current challenge. And the new industry standard is to automate the whole process, to automate the whole surveying process with the help of a drone or a ground vehicle. And we, as a company, would like to encourage this automated sensing technology with the help of a data set. So this poses us different challenges. Just like in an automotive scene, we have a complex and unique forest structures. Yeah, so there have been much more improvement on the automotive side, but on the non-automotive side, we don't have such a quite a data set. So we presented this in a Nature publication, and our paper was published. So this is our first public non-automotive data set using fisheye, LiDAR, and GPS ground truth. So the forest is the Hainich forest in Germany. It's located in the central part. We chose two forests, which is about 100 by 100 meters in size. Like I mentioned, it was captured in 3 different seasons in 3 different trajectories. As you can see in the image, we have blue, yellow, and green trajectories. So it was the same forest in 3 different seasons. And the red points are the labeled tree species and volume and the width and the diameter of the tree. So the different data points. So this was recorded using a field map system, which they have been using it on the TU Ilmenau University, where they provided different data points for the forest. So here's the setup overview. So just a standard custom UAV that we built with the LiDAR, 360 LiDAR, and 2 fisheye cameras. And the GPS data was recorded using an RTK GPS to get the ground truth odometry. So this ground truth odometry is a fused data of the IMU from the flight controller and the GPS data. A little bit more about the data set. So it's just 6 ROS packs. So our middleware was ROS2, sorry, ROS1. We had a total of about 1.5 hours of recorded data, about 200 GB in size. So the camera was operating at 15 FPS, and it was captured in RAW format. And it had no no IR filter, so the images that you saw were pinkish, so that was the reason. And the LiDAR was operating at 10 FPS, and the ground truth was also recorded at 10 FPS. And the fisheye was 190 degrees, and 2 fisheyes had a small overlap, so it was quite hard to make a stereo setup, which I'll explain later why. And we, for the challenge, split the data set 4:2, and 2 were for the test data sets and 4 for the training. So the main challenge was using this camera calibration that we use. So we use Puzzle Paint. I don't know how many of you know Puzzle Paint, but this is still in the beta, and they have this paper called why having 10,000 parameters is a better camera model than a normal parametric model. It's an interesting talk, interesting paper, so you can have a look at it in archive. So it was developed, it was published by ETH Zurich and Microsoft Mixed Reality Center in 2019, and it's still in beta. So what they propose is that you can get a much better camera calibration with a generic model, which will reduce your errors in case of end applications like VSLAM, depth estimation, and whatnot, in comparison to a parametric model like a double sphere or pinhole. So I don't want to dive deep into the tech, but the main flow is that you have a different looking pattern than the normal checkerboard. So you have these star segments, so you feature detect those segments and then refine it in the pattern space, the image space, and depending on the centric or non-centric camera model you choose, you can just fine-tune your parameters, and in the end you have a big file with 10,000 parameters. So these parameters are just the grid points on the image space where you can use the projection function to calculate pixel level intrinsic value. So that was the main challenge. So if you know how to use the projection and projection, which they have already provided the code in GitHub, you could have done a lot of different applications. So some of the experiments that we did with this data set is path planning, 3D mapping, monodepth estimation, and the most interesting one was the object detection classification. So we detected trees, which we already have ground point data points as ground truth. So we could just project it back into the 3D map that we generated using SLAM. And so this is sort of like auto labeling trees instead of manually, calculating distances between each of them. So here on the left, you see the projected points, the LiDAR points on the image space. So this was done using the projection function from the Puzzle Paint, just to show the feasibility of this camera calibration and how accurate that is. So I'll be presenting 2 baselines today. One is the monodepth baseline. When we published the paper in 2021, so we used the monodepth 2 as baseline, and this was pre-trained on Kitty, and then we directly inferred our data set. So we used the cropped and color corrected images. So we had to remove, so we have to use a color correction matrix to remove this IR, no IR filter, this pinkish flare. And our absolute error on the data set was 0.115. Yeah, so but the new baseline is now MIDAS, this mixing data sets for zero-shot cross data set transfer. So this was trained on 12 different data sets, including NYU Depth V2, which is a black and white closed environment, and Tardon Air, which is the simulated data set. So this MIDAS has seen different domains, and we were interested in see how it performs in a forest data set. And as you see the results on top right and top bottom right, you can even see the leaf foliage is being detected. So this is quite an interesting approach. And we don't have a baseline for it yet, but moving forward, I think we'll be pursuing this MIDAS data set. So for the odometry baseline, we use the LiDAR odometry in mapping, the advanced LiDAR odometry in mapping. And yeah, so this is our baseline for the odometry challenge. Yeah, so moving forward, unfortunately this year there were quite a lot of interest on the data sets. We had quite a bit of challenges. As I mentioned, using Fossil Brain was the biggest challenge, and we had insufficient submissions. So we decided to change the camera model to double sphere so that people can use it in different end applications like the VSLAM and mono depth estimation to get the scale and everything right. So our focus is going to be on molecular depth estimation in VSLAM for next year. Hopefully, we provide a better approach here. Yeah, so that's it. So we have a booth in the exhibit hall. So if you have any questions or if you want to see our live demo, you can come up there. Yeah. So some closing notes on this workshop. We encourage everyone to go and view the posters. All the posters are will be exhibited in the West Exhibit Hall. The numbers are from 178 to 192. Please make sure to check them out. Thank you.
Anybody didn't get a t-shirt?
Yeah, we have quite a bit of t-shirts.
I don't know where they bought them in.
So this concludes our workshop. Thank you, everyone. Thank you, everyone from the remote side.